Softwar by Jason P. Lowery, produced by Parker Banks at pbanks.net and youtube.com/pbanks. Novel computer theory about Bitcoin. Satoshi opened a portal from the physical realm into the digital realm, and energy began to flow into cyberspace, bringing life to a formerly dead realm consisting of only shadows and ghosts, bringing conservation of energy and matter, objectivity, truth, time, and consequence into the digital realm, delivering property rights, freedom, and sovereignty. Michael Saylor. Following the operational success of Bitcoin, several new computer theories regarding physical cost function protocols, aka proof-of-work protocols, have emerged. Just as new theories emerging throughout the early 1930s eventually became foundational to mainstream computer science, today's new computer theories regarding physical cost function protocols could one day become foundational to mainstream computer science as well. The goal of this thesis is to present an overarching, grounded theory on the socio-technical implications of physical cost function protocols and to understand how they could influence cybersecurity and national strategic security. The core concepts of this overarching theory are grounded to more technically detailed theories discussed in this section. Some of these ideas were inspired from data collection, but others are completely original. The most important takeaway from this technical discussion is that Bitcoin, the system, may not be special because it represents a new type of software, but because it represents a new type of computer. The author believes that Bitcoin represents the invention of what he calls a planetary state mechanism. Computational inefficiency has complex emergent benefits that few understand. What we obtain too cheap, we esteem too lightly. Thomas Paine. As of this writing, the fastest operational computer can transmit data at a rate of 1.84 petabits per second, making it fast enough to transmit the entire world's internet traffic in well under 3 seconds. This type of speed is possible because an unspoken assumption of computer engineering is that we should endeavor to build more physically unconstrained and energy-efficient state mechanisms with larger and larger state spaces so they can process as many bits of information as quickly and as cheaply as possible. Here's an interesting question. What's the slowest and most energy-inefficient computer in the world? Why don't we measure that or celebrate that machine? Rarely do engineers discuss the strategic value of endeavoring to biggest, slowest, and most energy-intensive computers with smaller and more physically restricted state spaces that have extremely difficult-to-change state mechanisms. Generally speaking, computational slowness and energy inefficiency are not valued. Few seem to recognize the benefit of creating intentionally costly bits of information. Notably, few articles are written by engineers celebrating how much power a computer had to consume to change its state or to send a command. There seems to be a universal bias for smaller, faster, and more energy-efficient computers because of an unspoken assumption that such devices are always better for every possible computing application. Incidentally, one of the rare groups of people who appear to understand the value of superfluously difficult computing and to celebrate how computationally expensive it is to transfer, receive, and store bits of information are Bitcoin enthusiasts. This is noteworthy. Bitcoin enthusiasts have emerged as iconoclasts who are not only unapologetic about the Bitcoin computing network's superfluous energy usage, they also celebrate how computationally difficult it is to run the Bitcoin network. Why do these people consider Bitcoin's extreme computational difficulty to be a virtue, while mainstream computer scientists appear to be adopting a stance that Bitcoin's difficulty is somehow bad? Leveraging the planet's global power infrastructure as a physically decentralized and thermodynamically restricted computer. Recalling the core concepts presented earlier in this chapter, modern computers are stored program general-purpose state mechanisms. Computers work because engineers learned how to apply symbolic meaning, for example Boolean logic, to physical state changes created by miscellaneous state mechanisms, by inventing a new language called machine code. One of the main reasons why machine code is so remarkable is that it allows people to convert practically any physical phenomena into bits of information that can be transferred, received, and stored using practically any form of physical state-changing mechanism. The key takeaway from this deep dive into computing was to develop a foundational understanding that thanks to machine code, practically any state-changing phenomena in nature can be utilized as a programmable computer, as well as a medium through which information can be transmitted and received by a computer. This explains why the physical form of general-purpose stored program computers has been able to change so dramatically over time. Whereas early computer engineers like von Neumann worked with massive machines and large plug boards, modern computer engineers work with microscopic floating gate transistors on circuits smaller than a fingerprint. The size, weight, and energy requirements of computers have changed dramatically over the years as computer engineers discover new ways to manipulate their physical environment. Nevertheless, machine code has remained the same. The past 80 years of computer engineering could be generalized as a search for the fastest and most energy-efficient state-changing phenomena. The primary goal of computer engineers has been to build cheaper, faster, smaller, and more energy-efficient state mechanisms. State mechanisms with larger state spaces are treated as though they are unquestionably better because they have more memory. Likewise, state mechanisms with easier-to-change states are treated as unquestionably better because they are cheaper and faster to operate. Generally speaking, the ability for computers to transmit more data, receive more data, and store more data on increasingly smaller devices is universally considered better. There has been little consideration if it would be useful to reverse optimize the design of a computer. Computer engineers' obsession with faster, cheaper, and smaller computers is what drove them to turn the fastest-known movable physical phenomena in the universe into a physical state-changing mechanism for use in computers: light. The reason why computer engineers have successfully managed to build computers which can process 1.84 petabits of information per second is because they leverage light itself as the state-changing mechanism to encode, transfer, receive, and store bits. As of this writing, the fastest computer chip works by encoding bits of information into light by applying machine code to modulated amplitude, phase, polarization, and wavelengths of transmitted light. Just as it is possible to create faster and more energy-efficient state mechanisms by leveraging faster and more energy-efficient phenomena of the natural environment, it should also be possible to create larger, heavier, slower, and more energy-intensive state mechanisms by taking advantage of the larger, heavier, slower, and more energy-intensive physical phenomena of our natural environment. All a computer engineer would need to do is find the appropriate physical state-changing mechanism and then apply Boolean logic to it. We have now established two key points that are essential to understanding the computer theory behind protocols like Bitcoin. The first key point is that people with their extraordinarily gifted capacity for abstract thinking can apply the Boolean logic of machine code to practically any physical state-changing phenomena to turn it into a programmable computer. The second key point is that for decades, computer engineers have been operating under an unchallenged assumption that smaller, lighter, cheaper, faster, and more computationally and energy-efficient computers are always better for computing applications. There has not been significant research towards exploring the idea that there could be major, complex, emergent benefits to designing and building a massive-scale, heavy, slow, expensive, and energy-intensive computer. Planetary-scale computation is theoretically feasible, and Bitcoin could be its operating system. A Los Angeles-based think tank called the Berggruen Institute has a program called Antikythera, named after the famous Antikythera mechanism, considered by many to be the earliest computer ever discovered. One of the primary goals of the Berggruen Institute's Antikythera program is to become a global leader in speculative philosophy surrounding the socio-technical implications of planetary-scale computation, to including the geopolitical impacts of planetary computation and what its underlying platform infrastructure might look like. In their view, planetary-scale computing could have extraordinary impacts on human society, including mind-bending implications like planetary sapience. If artificial intelligence were to reach a point where computers became sapient, and we were to combine this technology with a planetary-scale computing platform, then it is theoretically feasible for the planet itself to become sapient and self-aware of its own existence. Many of the Antikythera program's speculative philosophies about planetary-scale computing are outside of the scope of thesis, but the purpose of mentioning it is to illustrate the point that planetary-scale computing is a legitimate concept that is actively being investigated by organizations that influence public policy. It isn't really a matter of whether planetary-scale computing can be done, because we already know from computer theory that the Boolean logic in machine code can be applied to practically any physical state-changing phenomenon, to include the planet itself. It's pretty straightforward that planetary-scale computing could be done. Instead, the mystery surrounding planetary-scale computing is devoted to figuring out how it could be done, particularly what physical state-changing mechanism would be used and how its operating system would work. It's theoretically possible that Bitcoin could be emerging as the base layer operating system for a planetary-scale computer. This would mean that Bitcoin, the system, doesn't just represent a new type of software protocol, it represents a new type of computer. A new type of computer called a planetary-scale computer. If this theory is valid, then global adoption of Bitcoin simultaneously represents the global adoption of a planetary-scale computer. The exact thing which speculative philosophers like the Berggruen Institute's Antikythera program theorize would have drastic geopolitical implications. It turns out the natural environment outside of our computers is filled with circuitry and physical state-changing phenomena that could be utilized for large, heavy, slow, expensive, and energy-intensive computing applications. Our surrounding environment is filled with state-changing phenomena that can encode, transfer, receive, and store machine-readable bits of information. It is therefore theoretically possible to utilize the surrounding environment and supporting infrastructure outside of our worldwide web of computers as a singular and superfluously cumbersome planetary-scale computer in and of itself. Theoretically, all we have to do is figure out how to 1. Control its physical state, and 2. Apply Boolean logic to it, which is precisely what Bitcoin already appears to do. Not only would it be possible to utilize the planet itself as a large, heavy, slow, and energy-intensive computer, the infrastructure and circuitry required to accomplish this has already been built. We call it the global electronic power grid. Herein lies a simple but profound idea. To create the world's largest, heaviest, most energy-intensive, and most physically difficult to operate computer ever built, we could simply utilize our planet's energy resources as the controllable physical state-changing mechanism of a planetary-scale computer, where the globally distributed electronic power grid serves as its circuit board. Bitcoin demonstrates that it's possible to create a computer program that is so computationally and energy-intensive that it can lead to material changes to the state of the surrounding physical environment outside of the computers running it. Computer programmers could theoretically apply Boolean logic to these environmental state changes, converting them into machine-readable bits of information that can be fed back into ordinary computers. These ideas are valid according to modern theories of computation. By turning the surrounding environment outside of our ordinary computers into a state-changing mechanism and then applying machine-readable logic to those state changes, a computer network like Cyberspace would be able to send bits of information and control signals into its surrounding environment, that is the planet itself, and receive control signals back from its surrounding environment. This technique would make it possible to convert the planet itself into a massive-scale and globally decentralized planetary computer by utilizing 1. The planet's energy resources as the state-changing mechanism, and 2. The global electric power grid as its motherboard. This would qualify as a planetary-scale computer that could be plugged into the existing internet, effectively adding the state of the planet's globally decentralized and thermodynamically restricted energy resources to the state space of cyberspace through the existing infrastructure of our global electric power grid. From a first principles perspective, it's a surprisingly simple concept. Cyberspace is, after all, nothing more than the state space of all the physical state-changing mechanisms plugged into it. And the global electric power grid is nothing more than a bunch of machinery that changes its physical state. But what could possibly be the benefit of turning the electronic circuitry outside of our internet into a programmable computer in and of itself, and then plugging it back into the internet? The benefit is that it would create a physically decentralized and thermodynamically restricted section of the internet over which agrarian society would be able to compete for control authority in a zero-trust, permissionless, and egalitarian way using a physical power competition. As a complex emergent benefit of that physical power competition, the global population would be able to gain and maintain decentralized control authority over that part of the internet. This is where the core concepts discussed in the previous chapter become critical to understand. With the invention of this type of planetary-scale computer, agrarian society would be able to use their own energy resources to battle for control authority over this planetary-scale computer, the same way all organisms in nature, including and especially modern agrarian sapiens, have always used physical power competitions to battle for control authority over resources. And as a complex emergent benefit of this ongoing electric power competition, agrarian society would be able to gain and maintain decentralized control authority over this new digital age resource. As established in the section Emergent Benefits of Warfighting, one of the primary value-delivered functions of physical power competitions, aka warfare, is physical decentralization of control over Earth's natural resources. There's no reason to believe this wouldn't also apply to power competitions for control over the natural resources comprising a planetary-scale computer. A planetary-scale computer like this could theoretically create a portion of the internet where no single person or organization has full control over it. Thus, they have no ability to fully control the bits of information transferred, received, and stored on it. This decentralized portion of the internet could be reverse optimized to be more expensive and energy-intensive to send, receive, and store every bit, giving it complex emergent behavior that no other computer connected to the internet would be physically capable of replicating. These features could become extraordinarily useful for digital-age societies which find themselves increasingly trapped under software-instantiated abstract power hierarchies, crowned by a technocratic ruling class of digital-age god-kings who wield asymmetric abstract power and control authority over the existing computers connected to the internet. Right now, these rulers must be trusted not to exploit people through cyberspace because the population has practically no infrastructure in place to physically constrain software or impose severe physical costs on people, programs, or institutions operating in, from, and through cyberspace. Digital Age society also has no ability to use physical power as the basis for settling online disputes or achieving online consensus on the legitimate state of ownership and chain of custody of property. All of this could theoretically change if society invented a planetary-scale computer that effectively converted the global electric power grid into part of the internet. In short, it's possible to think of several reasons why people would benefit from a physically decentralized and thermodynamically restricted state space of the internet created by a planetary-scale state-changing mechanism which converts our electric power grid into the motherboard of a planetary-scale computer. A planetary-scale computer could physically constrain other computers for improved security. Bitcoin enables conservation of energy in time and space because it enforces conservation of energy in cyberspace. Michael Saylor. The surrounding physical environment outside of our computers would make a very different kind of state mechanism in comparison to the ones inside our offices and our pockets. It would have very physically expensive to change states. It would require so many watts to change states that some populations would literally not have enough power to change the state of this mechanism. This would translate into computer commands that are not practically possible to execute, or bits of information that are not practically possible to replicate, alter, or exploit. In other words, it would create a mechanism that computers could use to physically enforce and physically secure computer programs. Open and egalitarian access to this type of special-purpose planetary computer could give digital-age society the ability to physically enforce their policies, physically constrain sensitive computer control signals, and physically secure valuable bits of information in a way that was previously not considered possible. Populations would be able to use it to impose severe physical costs on other people, programs, institutions, and even entire nations who try to systematically exploit them through their worldwide web of computers. This capability could only get more valuable as more people, institutions, and nations coordinate international operations via cyberspace, because they would be more vulnerable to the threat of those who keep trying to systemically exploit the Internet's existing architecture. Physically constrained computers translate directly into physically constrained computer programs as well as physically constrained computer programmers. In other words, it's possible to physically constrain people in, from, and through cyberspace. It doesn't have to be done kinetically in three-dimensional space using forces to displace masses. Therefore, a thermodynamically restricted planetary-scale state mechanism would likely serve as a key enabling technology for physical power projection in, from, and through cyberspace. As discussed previously, the ability to project physical power to physically constrain computer programs and computer programmers in, from, and through cyberspace is notably missing in the design schematics of today's Internet architecture. If people were to build a planetary-scale computer like the one described here and plug it into the Internet, this could not only usher in new approaches to cybersecurity, but it could also dramatically change our approach to digital-age national strategic security, particularly how it relates to securing digital information and enforcing digital contracts. As previously discussed, one of the most challenging aspects of software engineering and cybersecurity is the inability to apply physical constraints to unsafe control actions or to impose physical costs on belligerent actors. It would theoretically be possible to utilize an open-source, internet-accessible, planetary-scale computer to perform these functions. The key to doing this effectively would be finding a way to chain down or couple ordinary state mechanisms to this new planetary-scale state mechanism. In this design, the planetary-scale computer with superfluously difficult-to-change states would apply severe physical constraints and thermodynamic restrictions on the normal computers connected to it via cyberspace, as well as the programs running on them. A planetary-scale computer could dramatically improve society's global electric power grid. There's another major benefit of utilizing a planetary-scale state mechanism as a large, heavy, slow, and energy-intensive computer. If society were to create a planetary-scale computer which utilized global energy resources as its state-changing mechanism, akin to transistors, as well as the global electric power grid as its circuitry, akin to a motherboard, then society could theoretically unlock the benefits of Moore's law for our energy infrastructure. Engineers love making their systems more efficient, particularly their computer systems. As previously mentioned, computer engineers are obsessed with optimizing their computer systems to make them faster, cheaper, and more energy efficient. This phenomenon is so predictable that we colloquially refer to it as Moore's law. If society created a planetary-scale computer, then populations would naturally seek to improve the speed and efficiency of this computer's circuitry. Societies might search for cheaper and more abundant sources of energy with more optimized infrastructure designs, so they could make their portion of the planetary-scale computer faster and more inefficient. There would also be an incentive to do this to gain a competitive edge in the form of more control authority over the planetary computer as a whole. These dynamics would create a counterintuitively beneficial feedback loop for society. The wide-scale adoption of a deliberately large, heavy, slow, and energy-intensive planetary-scale state mechanism would motivate society to try to continuously improve it by creating faster, more efficient, and more optimized electric power infrastructure. In other words, the complex emergent benefit of turning the global electric power grid into the circuit board of a planetary-scale computer would be to unlock Moore's law for the global electric power grid. By simply turning the power grid into a computer chip, society would be able to utilize its insatiable drive for faster and more efficient computer chips to create a faster, more responsive, and more efficient power grids. Software could utilize the environment outside of our computers as a computer in and of itself. With the potential benefits of a planetary-scale computing fresh in our minds, the reader is invited to re-examine physical cost-function protocols like the one invented by Adam Back, to further understand the author's assertion that Bitcoin could function as the operating system of a planetary-scale computer. There is a subtle but extremely important difference to emphasize between regular computer programs and physical cost-function protocols, aka proof-of-work protocols. Regular computer programs are designed to produce a single physical effect, a materially inconsequential transistor state change inside the circuitry of an ordinary state mechanism. However, physical cost-function protocols like Bitcoin are designed to produce an additional physical effect. Not only do they create transistor state changes inside of ordinary computers, they're also explicitly designed to create materially consequential state changes in the surrounding physical environment outside of our computers. It's incontrovertibly true that physical cost-function protocols like Bitcoin are so energy-intensive that they can directly influence the shape and structure of the surrounding electric power grid, a feature that has made Bitcoin infamous as a superfluously inefficient protocol by people who don't understand the complex emergent benefits of this design concept. Therein lies the key difference between normal software and Bitcoin that many people overlook. It's the fact that Bitcoin creates such a substantial physical change to the state of the environment outside of the computer on which it runs, which makes Bitcoin so extraordinarily different and unique compared to all other types of software. People mistakenly believe that Bitcoin's substantial energy usage is a bug, but it's actually its primary value-delivered feature. The physical state changes of the surrounding environment produced by physical cost functions manifest themselves as deficits or vacuums of electric power, which must be filled by electric power producers connected to the global electric power grid. This quantity of electric power represents a continuous time signal that can be transferred, received, modulated, digitally sampled, and stored as digital information, just like any other power-modulated electromagnetic signal. The primary differences are simply power intensity and production cost. Just like the world's fastest computer chips transmit, receive, modulate, sample, and store electromagnetic signals in the form of electromagnetic light waves with low power intensity and low production cost, physical cost-function protocols convert the electric power grid into a giant global-scale circuit board which can transmit, receive, modulate, sample, and store electromagnetic signals in the form of large quantities of electric power with comparatively giant power intensity and production cost. From a first principles perspective, it's the exact same infrastructure, circuitry, the exact same physical phenomena, electromagnetic signals, and even the exact same design concept, converting modulated electromagnetic signals into bits of information, but reverse optimized. Instead of using gradually smaller circuitry and smaller amounts of electromagnetic power, Bitcoin uses gradually larger circuitry and larger amounts of electromagnetic power. Using systems thinking, we can see that physical cost function protocols like Bitcoin function as a signal generator and modulator which send digitizable signals to a planetary-scale computer comprised of the global electric power grid. At the same time, physical cost function protocols also function as a signal processor which digitally samples signals received from the planetary scale computer. The signals sent to the planetary computer take the form of large electric power deficits created by the computer network running the cost function protocol, that is, the computers running Bitcoin, which can be modulated as desired by simply changing the difficulty of the solving the cost function's hashing algorithm. The signals received from the planetary computer take the form of a digitally sampled proxy measurement of the quantity of electric power consumed by the network. For physical cost function protocols like Bitcoin, computational power is sampled by measuring the average hash rate over a specified time interval. In other words, instead of sampling the modulated electric power drawn from the electricity grid, Bitcoin samples how many calculations are being made by the computer network running it as a directly proportional proxy measurement. Physical cost function protocols appear to utilize the planet itself as a programmable computer, where the globally decentralized power grid functions as its motherboard through which it sends, stores, and receives digitized information. These protocols can adjust the difficulty of their hashing algorithms to produce a modulated continuous time control signal in the form of a modulated quantity of electric power drawn from the surrounding physical environment. These protocols appear to be able to digitally sample the power signal they receive from the environment and turn them into a machine-readable, discrete time signal. These digitized signals are broadcasted to regular computers connected to the internet as regular bits of information, which can then be abstracted by computer programmers as anything they desire, just like all bits of information sent across the internet can be abstracted as anything the imagination is capable of thinking of. The bits can be described as a transferable object, like a proof of power receipt, with countless names like digital energy, bitwatts, or bit power. They could also be called stamps, tokens, spoons, coins, bit stamps, bit tokens, bit spoons, or perhaps even bitcoins. As always, what people call the bits of information passed across computers is semantic and arbitrary. It literally doesn't matter because bits are not matter. What makes the bits produced by physical cost functions matter is not their name, but the matter used to create them. In other words, what is happening under the hood of physical cost function protocols at the state mechanism level is what matters, because it's materially different than what happens under the hood with other software at the state mechanism level. There are very real, very meaningful systemic differences between the bits of information created, transferred, and stored by normal computers and the bits of information created, transferred, and stored by a planetary computer. The primary difference is that these two very different kinds of bits of information have been reverse optimized. Whereas bits of information from a normal computer are optimized to be as cheap and easy as possible to produce, transfer, and store, the bits of information from a planetary scale computer are optimized to be as expensive and difficult as possible to produce, transfer, and store. It's the exact same technology and the exact same digitization process, but reverse optimized. Here we can begin to appreciate what could eventually become recognized as a primary implication of physical cost function protocols like Bitcoin. Bitcoin appears to set a precedent within the field of computer science by being the first globally adopted software to utilize the planet itself as a state mechanism, that is, computer, for the explicit purpose of making bits of information increasingly more difficult to create, transmit, receive, and store. Physical cost functions protocols accomplish this by creating state changes in the surrounding physical environment outside of the microchips contained within ordinary computers. They apply Boolean logic to massive quantities of electric power drawn from the local environment, treating the globally distributed electric power grid as if it were a state-changing circuit board. By applying Boolean logic to the power grid, people convert large and expensive quantities of physical power into bits of information and feed that information back into our regular computers via the internet. People then use that information to affect state changes inside their ordinary computers. The result of this activity is a capability which does not appear to have existed before. The ability to impose severe physical costs and thermodynamic constraints on people, programs, and computer programmers operating in, from, and through cyberspace in a zero-trust, egalitarian, and permissionless way that no person or organization can fully control. People don't appear to appreciate how special physical cost-function protocols are because they are making the tacit assumption that all bits of information are the same. They think the bits produced by Bitcoin are the same as the bits produced by any other type of software. From a technical perspective, it's true that the bits produced by Bitcoin are generally the same as the bits produced by other software. In both cases, people are applying Boolean logic to a modulated electric signal. People aren't paying attention to what's happening under the hood, down at the foundational layer of the tech stack, the state mechanism itself. Without paying attention to what's happening under the hood at the state mechanism level, it's hard to see how the bits produced by proof-of-work protocols like Bitcoin are special because they have been reverse-optimized, giving them unique properties that are physically impossible to replicate by ordinary computers. Because people don't look under the hood, they overlook the fact that Bitcoin converts large and expensive quantities of physical power into bits of information. Physical power is converted into bit power, giving people the ability to wield real power in the abstract domain of cyberspace while retaining the beneficial systemic properties of physical power, for example, cost, scarcity, decentralization, and thermodynamic restrictions that can't be replicated by transistors in ordinary state machines. With physical cost function protocols like Bitcoin, the boundaries separating the circuitry inside of our computers and the circuitry outside of our computers disappears. Our microchips and our power grid become one in the same technology, but headed towards opposite sides of the optimization spectrum. Gradually, less materially consequential transistor states on microchips represent the side of the computational engineering spectrum that is being optimized to be as small, light, fast, and efficient as possible. Gradually, more materially consequential quantities of electric power drawn out of the global electric power grid represents the side of the computational engineering spectrum that is being optimized to be as large, heavy, slow, and energy-intensive as possible. The result? Very different emergent behavior. With proof-of-power protocols like Bitcoin, two very different worlds are bridged together into one combined system. Our planet's largest energy producers become equivalent to state-changing transistors on a giant global-scale transnational general-purpose computer over which no person or organization can afford to have complete and unimpeachable control. Agrarian society itself becomes a living, breathing part of the Internet's hardware. As a result of this bridge, the abstract things we encounter in cyberspace no longer exclusively represent a complex emergent effect created by cheap and materially inconsequential transistor state changes on a microchip. They could also represent expensive, materially consequential state changes in our surrounding physical environment that we can independently verify by simply observing the state of our civilian infrastructure. Physical cost function protocols, aka proof-of-work protocols like Bitcoin, therefore bridge our surrounding physical environment to cyberspace by effectively converting our surrounding physical environment into the state space of a computer. In other words, Bitcoin converts our three-dimensional space into a section of cyberspace. For the first time, agrarian society has zero trust and egalitarian access to physically constrained and thermodynamically restricted bits of information because the underlying state mechanism is physically constrained and thermodynamically restricted. We can pass these bits of information across cyberspace and use them however we want to use them to give our legacy cyber systems complex emergent behavior, for example, physical scarcity, decentralization, and zero trust control that is otherwise physically impossible for computers to replicate in cyberspace. Physical cost function protocols like Bitcoin therefore appear to function as both an operating system for a planetary scale computer as well as an application programmable interface, API, between our computers and the planetary scale computer, aka power grid, into which our computers are plugged. By creating this special planetary-scale computer, people appear to be adding a new, unique, physically constrained and thermodynamically restricted state space to cyberspace that has never been seen before, and it's leaving people confounded. They don't know how to describe what they're seeing because they've never seen anything like it. Bitcoin appears to be bridging our shared objective physical reality to virtual reality by turning the planet itself into a computer which can be programmed and plugged back into the internet. This could theoretically allow people to import the physically constraining and thermodynamically restrictive properties of our surrounding physical environment into cyberspace so that we can create real-world, materially consequential effects in, from, and through cyberspace. As engineers like Saylor have observed, proof-of-work protocols like Bitcoin appear to have opened a portal between the physical realm and the digital realm. In so doing, these protocols appear to be importing properties from one reality to the other in a manner that people apparently didn't think was possible. Programs running on a planetary-scale computer could program human civilization. Yet another potential benefit to be gained from turning the global electric power grid into a planetary-scale computer and then plugging it into the internet is that it would effectively create a bridge between the virtual reality of cyberspace and the real-world objective reality of our surrounding physical environment. The state changes of a planetary-scale state mechanism would represent materially consequential changes in shared objective physical reality as opposed to materially inconsequential and virtually undetectable state changes in microscopic transistors. By utilizing large quantities of energy drawn from the environment as a state-changing mechanism and running computer programs on it, this would cause software to have a highly path-dependent and irreproducible realness to it that ordinary computer programs running on basic computers simply cannot replicate. By learning how to utilize the planet itself as a programmable state mechanism, abstract concepts in computer programming are no longer strictly abstract. Computer programs would be capable of changing the physical state of the surrounding environment in substantial ways, giving software emergent behavior that is physically impossible to replicate by ordinary computer programs running on ordinary computers. The programs we run in cyberspace wouldn't just manifest themselves as images on a computer screen, they would begin to include major physical changes to the state of our surrounding three-dimensional environment, namely our global electric power grid architecture. This has already started to happen with Bitcoin. Instead of the images on our screens changing as we run our software, the infrastructure of agrarian society would change as we run our planetary-scale computer software. In essence, the software running of a planetary-scale computer would have the ability to program society itself. From a metacognitive perspective, turning the environment into a programmable computer would be a repeat form of bidirectional abstract thinking and symbolism discussed in the previous chapter. The symbolic meaning, Boolean logic, that sapiens apply to physical changes in shared objective physical reality would influence their shared abstract reality, and vice versa. By utilizing a planetary-scale computer that converts our global civilian infrastructure into a shared state-changing mechanism, the emergent behavior of the software running on that planetary-scale computer wouldn't be strictly virtual. The effects of planetary-scale computer software would correspond to real, meaningful physical changes of the observable universe in front of our eyes, in addition to changes in the imaginary world behind our eyes in the virtual domain of cyberspace. Once again, our abstract belief systems, our virtual reality, would change our behavior in physical reality. Except this time, our virtual reality would be the bits of information passing across the state space of cyberspace corresponding to the planetary-scale computer we created. The idea of using planetary-scale computing software to program how humans behave and structure their surrounding environment sounds remarkable. But when we take the time to reflect upon human metacognition and the concepts introduced in the previous chapter, we can see that this is actually ordinary human behavior. Human society already operates under large-scale consensual hallucinations. Society's abstract belief systems already dramatically influence social behavior as well as the shape and structure of our physical environment. The wide-scale adoption of these shared abstract belief systems already explains why societies organize into imaginary abstract power hierarchies like nation-states and then physically compete in wars. Nation-states are nothing more than shared virtual reality. They don't exist anywhere except within our collective imaginations. Therefore, humans have already adopted the habit of letting virtual reality govern their behavior on a global scale and influence how they structure civilization. Software running on a planetary-scale computer would essentially represent the exact same phenomenon, a common belief system that influences the shape, structure, and behavior of society itself. Proof of power protocols could double as proof of real protocols. Planetary-scale computers could also function as a grounding device which grounds elements of our shared virtual reality, cyberspace, to physical reality, three-dimensional space. Large quantities of physical power represent something real, path-dependent, and materially substantial. When large quantities of physical power are used to transfer digitized information across the internet, then proof of that power expenditure doubles as proof of materially irreproducible state changes in shared objective physical reality. In other words, proof of power protocols represent proof of real. After having reflected in the previous chapter about human metacognition and how sapiens detect if something is real, section How to Detect If Something is Real, the concept of using proof of power to represent proof of real in cyberspace makes perfect sense. Sapiens already use proof of power protocols like poking, pinching, or touching to prove or verify realness. Proof of real protocols are necessary because sapient neocortices are so effortlessly gifted at abstract thinking that it can be challenging to distinguish between real-world things and imaginary things. If a person ever finds themselves in a situation where they need to verify if something they encounter is real, the common protocol is to reach out and try to poke the thing. A key insight into the poking, pinching protocol is that it is fundamentally a proof of power protocol. When someone reaches out to touch an object to verify if it's a real thing rather than an imaginary thing, they are technically searching for a power signal. They're looking for the presence of watts. To poke something is to use energy to apply a force to displace mass across space and time. When someone pokes an object, they project power, aka watts. If the thing they're trying to poke moves or exerts an equal and opposite amount of force back at its observer, then the observer gains a cross-referenceable sensory input, aka synaptic feedback, needed to tighten their consensus that the thing they see does indeed physically exist and is not just a figment of their imagination, hence why companies are working on synaptic feedback systems to make virtual reality experiences feel more real. Why is a power signal so important for making online experiences feel more real? Because power is comprised of the core components of physically objective reality: time, space, matter, and energy. If a person can verify that power is present, then they can be much more confident that what they see is from the domain of physically objective reality, because they have verified to the best of their ability that the core components of objective reality are verifiably present. The object moved when it was poked, or the object pushed back. Therefore, the object must be real. How humans use proof of power protocols like poking and pinching illustrates a glaring capability gap for humans operating in, from, and through cyberspace. Cyberspace is a virtual reality. Virtual reality is, by definition, imaginary reality. When sapiens currently operate in cyberspace, everything they see represents nothing more than abstract meaning assigned to the state space of all the state machines connected across the internet. Connect billions of state machines together, and you get an incalculable number of states and state changes. Sum together the abstract meaning of that incalculable number of state changes, and you get the infinitely expanding imaginary reality of cyberspace. This domain is getting infinitely larger, faster, and cheaper to build. As this happens, cyberspace becomes infinitely more marginalized. When people operate online, their neocortices are deprived of cross-referenceable physical sensory inputs needed to verify realness. They have no way to generate a proof of power signal on their own, thus no way to produce a cross-referenceable sensory input to use as a proof of real signal. Synaptic feedback systems don't help with this because they're equally as artificially generated as the symbols on a screen or the sounds from computer speakers. Without being able to manually generate a proof of power signal by users on their own in a zero-trust way that can be independently validated, nothing in cyberspace is capable of being validated as physically real or consequential. Cyberspace becomes strictly an imaginary dream state, nothing but abstract meaning applied to bits of information stored as inconsequential state changes inside an infinitely expanding state space. The abstractions pile on top of each other to the point where nothing observable in cyberspace can be unique or special. They are just programmed to present the illusion of being unique or special. Sapiens arbitrarily chose to describe the internet as if it were a three-dimensional orientation of objects because that's the easiest and most intuitive way for us to explain the complex emergent behavior of something which otherwise takes an enormous amount of metacognitive effort to understand. The limitless potential of this dream space we are now starting to call the metaverse is an attractive place for some, but for others it's superficial and fake. As cyberspace expands, the meaning assigned to this place becomes increasingly ethereal and diluted. People come to realize that, ironically, despite the limitless potential cyberspace, it remains extraordinarily limited. It is capable of producing anything our imaginations are capable of thinking of, with one glaringly important exception: something real. Our computers can produce symbols, sounds, synaptic feedback, and complex emergent behaviors. Through false positive correlations and abstract thinking, people hypostatize the sights and sounds produced by these machines as if they were concretely real things. This learned habit of hypostatization doesn't mean that anything we see in cyberspace is physically real. What humans see online is nothing but synthetically generated images on an array of light-emitting diodes they put into their offices or carried around in their pockets. What humans hear online is synthetically generated air pressure waves produced by plastic cones, that is, speakers. Even our newly developed synaptic feedback systems are synthetically generated by some computer programmer who has control over that synaptic feedback system. Our computers never stopped being general-purpose state machines which produce artificial symbols and sounds and complex emergent behaviors via state changes. Without proof of real protocols like Bitcoin, these state changes are materially inconsequential, trivial to reproduce, thermodynamically unsound, and carefully designed by software engineers to present the illusion of something real but isn't actually real. We see and hear the same things online because our computers have been programmed to role-play the same things back to us. These computers are connected together and highly synchronized, producing artificial sensory inputs which feed our brains the same programmed sights and sounds. Once we receive these artificially produced signals, our neocortices apply the same abstract meaning to the same objectively meaningless and materially inconsequential patterns produced by these machines, creating a new form of shared abstract reality that we can see and explore together, a virtual reality we have named cyberspace. And behind all of these illusions are computer programmers who control them, computer programmers we must trust not to exploit us with their ability to conjure these illusions. The cyber stories we see online are entertaining and informative, but if we examine our behavior strictly from the perspective of shared objective physical reality, then we can see that all we are doing is behaving like an audience of people watching electromechanical marionettes acting out the same fictional performance for us. As we increasingly adopt the habit of ignoring the people who are pulling the strings of these marionettes, it becomes easier for us to believe that what we are seeing is something other than a well-orchestrated performance that was explicitly designed by someone in control over the illusion. This makes us gradually less capable of seeing that we can, and probably are, being oppressed by those who control these illusions. They are harvesting our data, they are experimenting on us to learn what drives our behavior, and they are using this knowledge to further their own agendas. It seems that we are beginning to lose sight of the lesson that the boy monk from the Matrix gave to Neo: there is no spoon. Operating in, from, and through cyberspace is akin to operating in a dream state with no time, energy, space, or mass. In Sailor's words, it consists only of shadows and ghosts. And behind that illusion is a person or organization who controls that illusion, a person or organization we implicitly trust not to conjure illusions which manipulate us for their own benefit. This trust is necessary because without proof of power protocols, aka proof of work, like Bitcoin, we neither have the ability to detect what's real, nor do we have the ability to apply physical constraints on those who might seek to manipulate us through the illusions they can conjure on our computers. The simple truth of the matter is that the world we see when we operate in, from, and through the current version of cyberspace exists in the human imagination only. The videos people watch, the text people read, the comments they see, the ads and images they encounter, even the results they get searching for something, are all carefully and deliberately programmed by computer programmers who wield unprecedented amounts of abstract power and control authority over people by virtue of their control over people's computers. Almost nothing about what people experience on the internet is random or even serendipitous anymore. All of it is being meticulously programmed by people who enjoy physically unrestricted control over billions of people's computers. That notification you got in the morning for a smoothie coupon was not serendipitous. Your apps continually harvest your phone's data and sell it to advertisers who know where you live, where you work, the routes you take, and the fact that you're going to be passing by that smoothie place you like in approximately 15 minutes. You are being manipulated. As people operate increasingly more in cyberspace, they find themselves with a unique problem. Everyone online is participating in a shared, abstract illusion where people have no way to verify if anything they're experiencing is linked to anything objectively real or even materially substantial. Practically all of the most popular software we rely on is attempting to influence our patterns of behavior for the personal benefit of that software's administrators, and they get away with it because there's currently nothing anchoring cyberspace to objective physical reality, nothing applying physical or thermodynamic restrictions on them. It's impossible to verify if anything seen online has real-world physical properties because people don't have the ability to poke or pinch anything. They have no proof of power protocol. At the same time, they are completely subject to the whim of the storytellers writing the scripts, the people pulling the strings, with no way to physically restrict them from global-scale systemic exploitation of cyberspace. Bitcoin potentially fixes this. With the arrival of open-source and globally scalable proof-of-power protocols, aka proof-of-work protocols, like Bitcoin, comes the arrival of a globally adoptable proof-of-real protocol. If a person wants to claim that their cyber abstraction has physically real and materially consequential properties like scarcity or physical cost or decentralization, then they must prove it with bits of Bitcoin. Otherwise, people have no ability to verify that what they see in cyberspace is anything more than just another illusion floating in an infinitely expanding sea of marginalized illusions trying to expropriate a population's most valuable bits of information, their behavioral data, and sell it to the highest bidder. The point is, proof-of-power protocols have metacognitive properties that could transform how people perceive cyberspace and operate in cyberspace in ways that we can't yet comprehend or fully appreciate because this technology is so new. To the author's knowledge, these pages represent the first time someone has even attempted to discuss these concepts together in formal academic literature. How humans perceive real is directly dependent on finding proof of power. Proof of power signals produced by physical cost-function protocols like Bitcoin could theoretically double as proof of real signals to serve the same function as kinetic power, that is, poking and pinching. When abstractions in cyberspace are accompanied by verifiable proof of real signals, they can have verifiable physical characteristics unlike any other abstraction in cyberspace, bringing what Saylor called the conservation of energy and matter, objectivity, truth, time, and consequence into the digital realm. At the same time, proof of power could also be used to legitimize or delegitimize computer programmers who otherwise have unrestricted abstract power and control over the illusions we see in cyberspace. Adding a physically constrained and thermodynamically restricted space to cyberspace. Combining these different theories together, we can see what advantages could be gained if someone figured out how to create a protocol which allows people to plug a planetary-scale computer into the internet. Bitcoin is special because it could represent the global adoption of the operating system for a planetary-scale computer, which converts our global electric power grid into a globally decentralized state mechanism under nobody's centralized control, that everyone on the planet is capable of operating in a zero-trust and permissionless way, so long as they're willing to project power. This planetary-scale computer would theoretically be capable of adding a unique and one-of-a-kind state space to cyberspace in comparison to the existing state space created by ordinary computers. This special state space would function as its own physically constrained and thermodynamically restricted space that no other state space in cyberspace could replicate, offering reverse-optimized properties that could be very useful for many different applications, particularly ones related to cybersecurity and keeping people safe against population-scale systemic exploitation and abuse of the Internet's existing architecture. The special state space created by a planetary-scale computer would be more materially consequential than other spaces in cyberspace, and people could use it to impose severe physical costs on other people by simply requiring them to operate or pass through this space. This state space could also link our surrounding physical environment to virtual reality in a way that previously wasn't considered possible, providing cyberspace with emergent properties that are physically impossible to reproduce using ordinary computers operating on the legacy, physically unconstrained, and thermodynamically unrestricted version of the Internet. As of now, these ideas are nothing more than theories grounded by the author's first principles approach to exploring the benefits of proof of power, aka proof of work protocols. However, if further scrutinization of these theories indicate they could be valid, then it's hard to understate the strategic value of the state space created by systems like Bitcoin. The bits of information passed across the Bitcoin system would represent bits of reverse-optimized information transferred, received, and stored by a planetary-scale computer. Bitcoin's coins would represent the underlying state space of this planetary-scale computer, an extraordinarily unique and strategically advantageous space within cyberspace. This would be similar to how there are unique and strategically advantageous positions inside of other domains. Just like canals and ports are strategically valuable spaces in sea, or Lagrange points are strategically valuable spaces in outer space, the physically constrained and thermodynamically restricted space of cyberspace could become among the most strategically valuable spaces in cyberspace. Owning a bit of Bitcoin's coins, which, if these theories presented in this thesis are valid, is really just an arbitrary name assigned to bits of information transferred and stored across a planetary-scale computing system, could represent owning an irreproducible piece of novel cyberspace created by society's first globally adopted planetary-scale computer. Moreover, because global leaders don't understand computer theory well enough to understand that the term coin is purely an arbitrary name, or because researchers aren't taking these theories seriously, this could mean that nation-states will become among the last institutions to establish a foothold in this potentially strategically vital space within cyberspace. This would upturn global power projection dynamics and dramatically restructure the digital age geopolitical environment exactly as planetary-scale computing theorists already believe will happen. Applying the strangler pattern to the Internet itself, starting with financial microservices. It is possible that in the future, people will not value objects in cyberspace unless they're anchored to our physical objective reality via verifiable proofs of power. Another way of saying the same thing is that in the future, people may not trust or value bits of information that are transferred and stored in cyberspace unless those bits of information are specifically derived from the planetary scale computer. In fact, this is already starting to happen, as people have already started not to trust or value financial bits of information unless they're derived from the Bitcoin computing system, which, the author theorizes, doubles as the operating system of the world's first operational planetary-scale computer. Why would people not trust or value bits of information that haven't been physically constrained or thermodynamically restricted, simply because they would not be anchored to anything verifiably real or materially consequential? People might one day come to understand that everything they encounter in the so-called metaverse is something physically unconstrained, thermodynamically unrestricted, materially irrelevant, and under the complete, unimpeachable control of some technocratic ruling class who can and probably already is exploiting these unconstrained and unrestricted bits of information. One day, civil society may learn that if they want to physically constrain and decentralize people's control over their computers in order to mitigate global-scale systemic exploitation and abuse of the Internet, they will have to learn how to utilize real-world physical power, aka watts, to countervail the imaginary power of their neo-god kings, aka software administrators, the same way agrarian society has always had to utilize real-world physical power to countervail the imaginary power of their god kings. Physical power has always been both the antecedent and the antidote to imaginary power. New physical power projection protocols like Bitcoin appear to be integral to the same power projection game agrarian society has always played, but in a new domain where digital age society is spending increasingly more of its time. If this cultural evolution were to occur at large enough scale, then the special state space added to existing cyberspace by systems like Bitcoin could one day become recognized as the foundational layer of the Internet, which grounds cyberspace to the physical constraints of shared objective material reality. This new, physically restricted version of cyberspace could become universally recognized as a place where computer programmers, with their immense abstract power and physically unconstrained control authority over people's computers, can no longer use it to exploit people's bits because it's too physically expensive. It is theoretically possible that people might start making a clear and pronounced mental distinction between two different versions of cyberspace with two very different kinds of bits of information transferring across them. One version of cyberspace would be physically secure against a technocratic ruling class of computer programmers and software administrators who have already demonstrated that, when left unphysically constrained, can and will deny people's bits, harvest people's bits, use people's bits to learn how to affect their behavior, and use what they learn to exploit or influence the behavior of entire populations at unprecedented scale. The other version of cyberspace would be the original version of cyberspace that we know today, the version of cyberspace where people don't have the ability to physically secure their bits of information because they have no ability to impose severe physical costs on people in, from, and through cyberspace who try to deny their right to transfer bits or who try to exploit them in many other ways, thanks to their having centralized control over those bits. In the newer version of cyberspace that is backed by proof of power, things would have verifiably real-world physical properties like scarcity and decentralization that would be physically impossible to replicate in the older version of cyberspace created by ordinary computers. In the new version of cyberspace, programs wouldn't be allowed to execute certain control signals unless they're backed by substantial proof of power, thereby physically constraining the reach and control authority of software-defined abstract power hierarchies. This would be a stark contrast to the older original version of cyberspace that is notably lacking proof of power, where all software abstractions would continue to not have verifiably real-world physical properties. In the legacy version of cyberspace, The abstract power and control authority of software-defined abstract power hierarchies would continue to remain physically unconstrained, and all of the clear systemic security challenges we have today would remain the same because the underlying architecture of the Internet would remain the same, namely the inability to impose severe physical costs or physical constraints. In the future, proof of work, aka proof of power, aka proof of real, aka physical cost function protocols like Bitcoin, could serve as the dominant mechanism used by digital age societies to map or anchor elements of the legacy version of the Internet to the new version Internet, thereby serving as the world's globally adopted proof of real protocol. Regardless of whatever arbitrary name people give to protocols like Bitcoin in the future, the point is that Bitcoin could become instrumentally more important than merely a financial system. Bitcoin has the potential to become integral to the development of a completely new Internet infrastructure and a completely new type of cyberspace. It is possible that what we are seeing with the global adoption of Bitcoin represents a strangler pattern playing out for the existing Internet architecture. We could be modernizing a large monolithic computing system right now by gradually replacing services performed on the legacy system with services performed on the modernized system. And it could just be that financial information exchange simply represents the first of many microservices to be performed on a modernized architecture of the World Wide Web. There is no second best. Air power is like poker. A second best hand is like none at all. It will cost you dough and win you nothing. George Kenny. Physical cost function protocols can't be replicated by ordinary computers and software. Another reason why it is important to point out what's going on under the hood with physical cost function protocols like Bitcoin is to illustrate how there are very meaningful physical differences between this technology and other computer programs. People who utilize proof-of-work protocols like Bitcoin are technically using a different style of abstract thinking than people who utilize regular computer programs. Without examining the underlying tech stack, it's impossible to see these differences or to appreciate how the abstractions used to describe objects like bitcoins have different systemic and complex emergent properties that are physically impossible to reproduce using other software running on other computers. When operating ordinary computer programs, people assign abstract meaning, for example Boolean logic, to transistor state changes in a state machine. However, when operating physical cost function protocols, aka proof-of-work protocols, like Bitcoin, people also assign abstract meaning to quantities of physical power. This means that the abstractions people use to describe the complex emergent behavior of ordinary programs are both physically and systemically different than abstractions used to describe systems like Bitcoin, even though they have the exact same semantic specifications. In other words, the bits produced by normal software using normal computers have physically and systemically different properties, which means the abstractions used to describe those bits also have physically and systemically different properties, even though they have the same name. It is physically impossible for a coin generated by an ordinary computer program to have the same complex emergent properties as a coin generated by a proof-of-work protocol like Bitcoin because they are physically different systems, in the same way that something which doesn't physically exist doesn't have the same complex emergent properties as something which does physically exist, particularly properties like being verifiably scarce or decentralized. Bits of coin created by an ordinary piece of software running on an ordinary computer can't have the same complex emergent properties as Bitcoin. From the software at the top of the tech stack, all the way down to the underlying state mechanism, Bitcoin is a fundamentally different computing system with physically different and reverse-optimized hardware, making it incomparable to traditional computing systems. When people normally refer to an object instantiated by ordinary software, they use machine code to apply abstract and symbolic meaning to transistor state changes inside a computer to convert them to machine-readable bits of information. The objects people refer to when they describe their computer programs do not physically exist. People arbitrarily choose to describe the complex emergent behavior of their computer programs using metaphors like objects to make it easier for other people to understand the intended functionality and design of their computer programs. For example, folder, trash can, cloud, string. In other words, there is no spoon. All that physically exists is a physically unrestricted and infinitely expanding state space of countless state machines plugged together. Countless transistors are added together on circuit boards, and the state of those transistors is what we abstract so-called objects. Underneath all those abstractions and metaphors is nothing but people converting transistor state changes to bits using new types of language. Physical cost function protocols, aka proof-of-work protocols, like Bitcoin, work entirely differently. When people describe the real-world physical cost of solving a physical cost function protocol as if it were a quantifiable object, for example, a proof, receipt, stamp, coin, or token, they're using an abstraction to describe what is actually a real, meaningful, physically scarce, physically constrained, thermodynamically restricted, path-dependent, and irrevocable quantity of physical power drawn from shared objective physical reality. Therefore, whereas ordinary computer programs can only present the illusion of physical costs, physical cost function protocols like Bitcoin produce real-world physical cost. Likewise, whereas ordinary computer programs can only present the illusion of scarcity and decentralization, Bitcoin produces real-world scarcity and decentralization because the underlying physical state-changing mechanism being converted into bits is, itself, physically scarce and decentralized. The physically costly quantities of real-world power utilized by protocols like Bitcoin double as machine-readable bits of information which can then be described as an abstract object. Thus, there's a substantial difference between the abstract objects produced by regular software and the objects produced by physical cost functions because the bits which comprise those objects are derived from physically different and reverse-optimized phenomena. These differences go undetected because people aren't paying attention to the underlying state mechanism. They're only paying attention to the software layer where everything looks the same, not the hardware layer where things are clearly different. The same object-oriented software abstractions refer to two completely different physical phenomena with completely different physical and emergent properties. As discussed in the previous section, the bits produced by ordinary computer programs have the exact opposite design intent as the bits produced by physical cost function protocols. Right now, people are treating these bits as if they're the same thing without taking the time to understand how these bits have been intentionally reverse optimized. One explanation for why computer scientists and software engineers keep overlooking these differences is because they've become accustomed to evaluating tech stacks from the top down, not the bottom up, so naturally they aren't going to detect that a new state mechanism has been added to the bottom of the stack. Additionally, it's possible that software engineering culture has become so accustomed to abstraction, information hiding, and ignoring everything below assembly language that they aren't inclined to recognize how proof-of-work utilizes a completely different state mechanism with properties that are physically impossible for non-proof-of-work systems to replicate. Physical cost function protocols, aka proof-of-work protocols, are simple. They convert watts to bits. When people utilize computing networks like the Bitcoin network, they take watts as their input and convert them into proofs of watts as their output, which people then abstract as if it were the same as any other type of abstract object instantiated by software. Computer and software engineers aren't taking the time to consider the major technical differences in the underlying physics, despite how observably different it is. Why do these major technical differences go undetected? The author hypothesizes that it could be because proof of work represents an unprecedented approach to computing that software engineers aren't recognizing yet because they have effectively been trained by their industries to ignore what's happening under the hood of their software by abstracting it all away. As previously discussed, computer programming is an enormously complex challenge. It is essential for computer programmers to reduce cognitive distance and lighten the metacognitive burden of software engineering as much as possible. Object-oriented software design is one of the most common abstraction techniques. An easy thing to do to reduce cognitive distance is to call the proof of power receipt produced by a physical cost function a receipt, or stamp, or token, or coin, and then to simply move on without taking the time to sort through the physical details. When computer scientists and software engineers do this, they tacitly treat the abstract object produced by a proof-of-work protocol, for example a Bitcoin, as if it were the same as any other abstract object produced by software, despite obvious physical differences in the underlying tech stack. Consequently, they miss the fact that Bitcoins are physically costly, constrained, and decentralized in a way that no ordinary software object can be. Probably the most famous example of people making this mistake is when they claim that proof-of-stake protocols can have the same complex emergent properties, for example decentralization, as proof-of-work protocols. What these people are overlooking is the fact that stake and work are physically incomparable because stake is an ordinary software abstraction for a normal computing system, whereas work is an abnormal software abstraction for a fundamentally different type of computer with a fundamentally different time of state machine. More on this in the following sections. Using abstractions like Bitcoin, critical information about the differences in underlying hardware is lost in the same way that critical information about the cloud is lost. As previously discussed, this is a recurring challenge of software engineering that negatively impacts security. The semantic ambiguity of software specifications is a well-known challenge with cybersecurity that can cause people to overlook vitally important security information. Like how storing sensitive information on the cloud means storing sensitive information on someone else's computers that you can't control. Just like the term cloud hides critical information about where bits of information are being physically stored, the use of object-oriented software abstractions like coin for proof-of-work protocols disguises the fact that the bits of information described as a coin represent state changes occurring outside of our computers, not inside of them. Because people don't understand this, they overlook highly unique properties of proof-of-work protocols which have a potential to change the game of cybersecurity or even change how humans perceive cyberspace. It is physically impossible for proof-of-stake protocols to replicate proof-of-work protocols. For what might be the first time since Newman's invention of stored program computing techniques, people are learning to use proof-of-work protocols like Bitcoin to program something other than state changes inside a state machine. The massive electrical power deficits produced and consumed by protocols like Bitcoin represent external state changes of the surrounding environment outside the boundary of our ordinary computers. This makes it possible to couple state changes inside a computer to state changes outside a computer, effectively bridging the cold, hard, shared objective reality of our physically constrained and thermodynamically restricted environment to the virtual reality of cyberspace. Proof-of-work protocols developed by computer engineers like Adam Back may represent the discovery of a programming technique that simultaneously changes the physical state of the physical environment outside of computers, as well as the physical state of the transistors inside computers, giving computer programmers a way to program the virtual environment and physical environment simultaneously. With this capability, the abstractions we use in cyberspace can reshape our surrounding physical environment, and then import the real-world physical properties of our surrounding environment, properties like physical cost, physical scarcity, and physical decentralization, into cyberspace. This can be done by simply building the infrastructure needed to convert watts into bits. These theoretics emphasize the point that Bitcoin represents a physically different tech stack from the bottom up. It has irreproducible, complex, emergent behavior because it uses a different base layer state mechanism that has been intentionally reverse optimized to produce more physically expensive bits rather than less physically expensive bits. This critical information about proof-of-work computing systems is hidden by the metaphors used to describe the software. This is not surprising considering how information hiding and abstraction is treated as a virtue within the field of computer science, as discussed in the section Software Security Challenge 5. Critical information about substantial technical differences that impact security often gets overlooked because of the arbitrary semantics used to emphasize different features of the software. Since the physical differences at the bottom of the tech stack are often ignored, many software engineers assert they can replicate the complex emergent properties, namely systemic security, of Bitcoin using regular programs running on ordinary computer hardware. Additionally, the general public commonly claims that the Bitcoin computing network is energy inefficient and that it should be replaced by something more environmentally friendly. The author believes these assertions are being made because people are missing the point that making a physically costly computer for the purpose of producing physically constrained and thermodynamically restricted bits of information is the primary value-delivered function of proof-of-work protocols. The point of the protocol is to create physically expensive bits, as physically expensive bits are useful for cybersecurity applications. The software engineering culture of abstraction and information hiding could explain the public misconception of proof-of-work protocols like Bitcoin. The information needed to understand the novel computer theory behind proof-of-work is lost in the metaphors. This explains why so many software engineers will claim to be able to replicate the complex emergent behavior of Bitcoin using metaphors like blockchains or cryptocurrencies that are ostensibly more energy efficient. These claims represent a lack of appreciation for power projection and the complex dynamics of reverse-optimized computing that is probably being perpetuated by a decades-old and well-established software engineering culture of not paying attention to the physical differences of the underlying tech stack. It's incontrovertibly true that Bitcoin has a far different physical signature than these other so-called blockchains. But computer and software engineers aren't taking the time to study why it's physically different and what that means. Probably the most famous illustration of this lack of appreciation for power projection and the novel computer theory behind proof-of-work protocols is amongst those who believe proof-of-stake protocols can replicate the same complex emergent behavior and be a more energy-efficient alternative. When people make these claims, they illustrate that they don't understand the point of proof-of-work. Proof-of-work and proof-of-stake are physically and systemically different technologies that utilize completely different, reverse-optimized state mechanisms that are practically incomparable no matter what arbitrary metaphors are used to try to categorize them as the same technology, that is, blockchain or cryptocurrency. For the same reason, it's not possible to claim that something which doesn't exist is equal to something which does exist. It's not possible to claim that proof of stake is equal to proof of work. The incontrovertible physical difference between these two protocols is that one is far more physically expensive in watts than the other one. These physical differences would imply that it's physically impossible for proof of stake to have the same complex emergent properties, namely physical cost, aka CA, as proof-of-work protocols. In other words, it should be clear to any observer that the bits of information produced by a proof-of-stake protocol cannot replicate the physical expense of the bits of information produced by a proof-of-work protocol, because that difference is directly measurable in watts. Therefore, the issue isn't that proof-of-work is too physically expensive. The issue is that people don't understand why physically expensive bits are useful, perhaps because they don't understand power projection dynamics and how physically expensive bits could be used to increase CA, thus decrease BCRA of our computer systems. In addition to not understanding why it would be useful to have physically expensive bits, the general public also doesn't seem to understand that stake is not a real thing, it's just a metaphor. Just like there is no spoon, there is no stake. The term stake is simply a metaphor for the special administrative privileges given to users who validate transactions. It's purely an imaginary concept, an object-oriented software abstraction that doesn't physically exist and therefore is physically impossible to verifiably decentralize. Stake, and consequently the special administrative privileges it represents, cannot be decentralized anywhere except exclusively within people's imaginations, because stake itself is an abstract concept. Proof-of-stake systems are what's known as decentralized in name only, Dino systems, because it's physically impossible to verify that stake isn't already under the control of a single person or institution. More on this in the next section. Another way to conceptualize the difference between proof-of-work versus proof-of-stake systems is to borrow from the concepts of power projection theory and rename these protocols proof-of-real power versus proof-of-imaginary power. Proof-of-stake is proof-of-imaginary power, aka proof-of-rank. A proof-of-stake system is yet another form of exploitable abstract power, where a select few people within a carefully encoded abstract power hierarchy get consolidated administrative permissions and control authority over an underlying resource. Therefore, a proof-of-stake, aka proof-of-rank or proof-of-imaginary power protocol, is functionally the same type of systemically exploitable rank-based belief system as a government rule of law, complete with the same kind of systemically exploitable voting logic. Moreover, proof-of-stake is clearly a plutocratic design where those who have the most Ethereum can also have the largest amount of abstract power, aka stake. Because they're functionally the same type of encoded abstract power hierarchy where a select few people control the underlying resource, that means proof-of-stake systems also have the same type of systemic security flaws as traditional governments and rules of law, plutocracies in particular. Additionally, because they're the same type of software running on the same type of computers, that means proof-of-stake systems also have the same kind of cybersecurity vulnerabilities that practically all traditional software systems have, namely the inability for users to physically, as opposed to logically, secure themselves against the systemic exploitation of encoded design logic. As proof-of-stake systems become more popular, the benefit to be gained by exploiting the special administrative privileges given to those who control the most stake, aka the BA, will increase. But the physical costs of attacking the system, aka the CA, will continue to remain fixed at practically zero. Thus, the benefit-to-cost ratio of systemically exploiting proof-of-stake systems, aka BCRA, will gradually approach infinity as more people adopt these systems. Slashing doesn't prevent this because the top stakers would clearly have the incentive and the means to slash users back. Moreover, slashing is a voting-based system that is endogenous to the system, which means it can, and most assuredly will, be systemically exploited by those who encoded the design logic, which incidentally are probably the same people who control the majority supply of stake. Ironically, proof-of-stake systems recreate the exact same type of systemically exploitable, abusable, trust-based abstract power hierarchy that it was ostensibly created to replace. Instead of creating a decentralized system, a proof-of-stake system gives unimpeachable, centralized control authority over the system to an anonymous group of people who own the most of some imaginary object called stake, which is really just another name for rank or administrative privileges. Instead of creating a decentralized organization, proof-of-stake systems like Ethereum have created a system that is capable of masquerading as a decentralized system because those who control the majority supply of stake can take advantage of disembodied nature of software to disguise how centralized and consolidated that stake is. To believe that proof-of-stake protocols can serve as a viable replacement to proof-of-work protocols is to believe that something which doesn't physically exist can have the same complex emergent properties as something which does physically exist. Proof-of-stake is yet another systemically exploitable belief system that people are adopting for what are often ideological reasons because they desire a viable replacement for physical power as the basis for settling disputes, establishing control authority over resources, and achieving consensus on the legitimate state of ownership and chain of custody of property. Ironically, this means that proof-of-stake systems represent the exact same style of abstract power and empire building discussed in the previous chapter, complete with the exact same style of ruling class wielding yet another type of asymmetric abstract power and control authority created by convincing a population to adopt the same belief system. To repeat the same point using the concepts introduced in the section Understanding Abstract Power, stake is nothing more than imaginary power masquerading as real power, watts. Like every other type of imaginary power that has been conjured up by people searching for a viable replacement to real power, stake is neither self-evident nor self-legitimizing. It's systemically endogenous to the software which instantiates it, making it highly vulnerable to systemic exploitation and abuse by the people who write the software. It's physically unconstrained and thermodynamically unsound, bounded, zero-sum, non-inclusive, inegalitarian, and non-attributable. This makes proof-of-stake protocols physically and systemically opposite from proof-of-work protocols. To believe that two physically and systemically opposing technologies can achieve the same emergent effect is equally as silly as the concepts presented in the previous chapter, where people believe that a man wearing a wig has the same type of power and achieve the same type of security as a woman firing the Gatling gun of an A-10 Thunderbolt II. To persuade people that proof-of-stake can replicate the same complex emergent properties, for example security, scarcity, decentralization of control, etc., as proof-of-work is, according to many, a fraudulent claim. Not surprisingly, the lead developers of the largest proof-of-stake system started a trend of marginalizing those who accuse him of being fraudulent as being Bitcoin maxis. The implication being that people who believe that proof-of-stake systems cannot claim to be decentralized or cannot have the same complex emergent behavior as proof-of-work protocols are closed-minded. Interestingly, this behavior of claiming that imaginary power can have the same properties as real power could be interpreted as precisely the same style of God-King abstract power building which motivates entire populations of people to willingly forfeit their real power for systemically exploitable imaginary power because they don't understand the complex physical and systemic differences between real power and imaginary power-based resource control structures. It even has the same moral, ethical and ideological motivations behind it. People who forfeit the use of proof-of-work protocols like Bitcoin in favor of proof-of-stake protocols like Ethereum are explicitly forfeiting their capacity and inclination to project physical power and impose severe physical costs on attackers because they're ideologically inclined to believe that Bitcoin's power expenditure is bad. This, of course, creates a window of opportunity for systemic predators to prey on these ideological beliefs, to convince the general public to forfeit proof-of-work protocols like Bitcoin in favor of alternative protocols where a select few anonymous people have systemically exploitable administrative permissions and control authority over the system via their large and physically impossible to verifiably decentralize amount of so-called stake. Just like they have been doing for thousands of years, people want to believe that proof of imaginary power protocols can sufficiently replace proof of real power protocols because they don't like the energy expenditure required to use real power as the basis for settling their disputes, establishing control authority over their valuable resources, or achieving consensus on the legitimate state of ownership and chain of custody of their property in a zero-trust, permissionless, and systemically secure way. As a result of this desire not to use physical power, we can see the exact same security vulnerabilities discussed at length in the previous chapter. People who are adopting proof-of-stake systems are adopting trust-based, permission-based, inegalitarian, and systemically insecure imaginary power hierarchies. History tells us what happens to these systems. They eventually become dysfunctional as the people with the most abstract power and control authority over the system start to abuse it, and users are incapable of stopping it because they made the mistake of believing that encoded logical constraints would secure them. The change from Ethereum 1.0 to Ethereum 2.0 created major systemic security vulnerabilities. One of the ways that I think about this in a more philosophical way is like proof of work is based on the laws of physics. So you have to sort of work with the world as it is. You have to work with electricity as it is, hardware as it is, what computers are as it is. Whereas because proof of stake is virtualized in this way, it's basically letting us create a simulated universe that has its own laws of physics. And that just gives us as protocol developers a lot more freedom to optimize the system around actually having all the different security properties that we want. If we want the system to have a particular security guarantee, then often there is a way to modify the upper state mechanism to also achieve it. Vitalik Buterin, the night of Ethereum's transition from proof of work to proof of stake. This section will repeat many of the concepts from the last section, but apply them more specifically to the context of the Ethereum computer network, which is currently the most widely adopted proof-of-stake network. This section summarizes arguments that have been made against the Ethereum network, most notably the argument that Ethereum developers are fraudulently claiming to be able to achieve the same level of security and decentralization as the Bitcoin network while eliminating the energy expenditure of proof of work. If the reader isn't interested in learning more about these arguments, they are encouraged to skip this section, as it repeats many of the concepts presented in the previous section. As discussed at length in the section Software Security Challenges, a primary challenge associated with cybersecurity is a lack of ability to apply physical constraints to software. Another challenge associated with cybersecurity, outlined in detail in section Software Security Challenge 5, is that because software is abstract, computer program developers use arbitrary and semantic metaphors to describe their software designs that are not technically accurate and often disguise critical information needed to understand how secure that software is. This is a systemic security vulnerability because it creates a window of opportunity to, sometimes intentionally, design exploitable design features into a given piece of software and then disguise those security vulnerabilities with disingenuous metaphors. Many have argued that this is what occurred with Ethereum's recent pivot from a proof-of-work security protocol to the proof-of-stake security protocol. By making this change, people who, not surprisingly, have been condescendingly labeled by Ethereum developers as Bitcoin maximalists, believe that Ethereum is disingenuously claiming that stake can provide the same systemic security properties as work. Using the concepts of power projection theory presented in this thesis, we can see that with the conversion from Ethereum 1.0 to Ethereum 2.0, developers converted the software from a physical power-based resource control system, constrained and secured by physics, to an abstract power-based resource control system without physical constraints or thermodynamic restrictions, thus dramatically changing the software's complex emergent security features and giving unimpeachably consolidated control authority over the system to Ethereum's lead developers and administrators. Ethereum's most famous co-developer Vitalik Buterin asserts their decision to remove physical constraints is actually good for cybersecurity because it enables Ethereum's developers to use encoded logical constraints to logically secure the system rather than using energy-intensive physical costs, aka watts, to physically secure the system like proof-of-work protocols do. Buterin's assertion not only contradicts decades of established principles in system security, it's also illogical. As one, it is physically impossible for encoded computer logic alone to fully replicate the emergent benefits of physical constraints, and two, computer logic alone is demonstrably incapable of preventing the systemic exploitation of computer logic, hence every software hack that has ever occurred. By changing from a proof-of-work, aka proof-of-real power security system, to a proof-of-stake, aka proof-of-imaginary power security system, not only has it become physically impossible to verify that Ethereum is a decentralized system, it has also created another type of software-defined, abstract power-based resource control hierarchy, which gives extraordinarily asymmetric abstract power and control authority over to an anonymous group of people who control the majority supply of stake. Ethereum users must necessarily trust that the people who control the majority supply of stake will not exploit or abuse it, and they are counting entirely on systemically exploitable encoded logic to secure themselves from this exploitation and abuse, because they are now physically powerless to secure themselves. When comparing the systemic changes which occurred when Ethereum changed from a proof-of-work system to a proof-of-stake system, we find that proof-of-stake creates a near-identical resource control structure as proof-of-work that is easy to misperceive as the same system. The controlled process, in this case the bits of information recorded by the blockchain, is the same, the controllers are the same, and the general structure is the same. The main difference is simply the type of power used. Whereas Ethereum 1.0 was a PPB resource control hierarchy that utilized real power, aka watts, Ethereum 2.0 is an APB resource control hierarchy that utilizes abstract power, aka stake. The reader should note that these are the same control structure models discussed in the section Abstract Power Hierarchies. As introduced through the concepts of power projection theory presented in previous chapters, it's easier to spot the systemic differences between Ethereum 1.0, a proof-of-work system, and Ethereum 2.0, a proof-of-stake system. Ethereum 2.0 is far more vulnerable to systemic exploitation from those who control the majority supply of Ethereum, whereas Ethereum 1.0 isn't. This exact same principle also holds true for other proof-of-work systems like Bitcoin. Bitcoin is not nearly as systemically vulnerable to users who have the most BTC, because owning BTC doesn't give users the same type of special administrative privileges over the system, namely validation rights, as people's Ethereum give them in the Ethereum 2.0 control structure. Another way to illustrate this systemic security flaw is to revisit the threat posed by domestication. From a functional perspective, proof of stake is a repeat of the domestication hazard discussed in the sections Domestication is Dangerous and Dysfunctions of Abstract Power. By switching from proof of work to a proof of stake system, Ethereum users have allowed themselves to give control authority to people with abstract power rather than those with real power, aka watts. As a result of making this change, users tacitly forfeit their ability to gain and maintain special administrative privileges, namely validation rights, over the system in a zero-trust, permissionless, and egalitarian way that can be verifiably decentralized simply by projecting their own real power. People who adopt proof-of-stake systems forfeit their own capacity to tap into an unbounded supply of non-systemically exploitable physical power, which they could use to impose severe physical costs on other users who exploit or abuse their special administrative privileges. To put it simply, the BCRA of exploiting the special permissions granted to users with stake will only increase because it's physically impossible for users to increase their CA. A leading cause of people's confusion about the difference between proof of stake and proof of work is that they don't understand the physical and systemic differences between what people arbitrarily call work and what people arbitrarily call stake. The key insight that people are missing is that work refers to real-world physical power, aka watts, whereas stake is an arbitrary semantic expression given to an imaginary object-oriented software abstraction. This subtle but key difference has important implications because it means that proof of work and proof of stake systems are incontrovertibly different technologies down to the base layer state mechanism, making it physically impossible for proof of stake systems to replicate the same cybersecurity properties as proof of work systems, most notably the ability to keep special administrative privileges physically decentralized and impeachable. If stake doesn't physically exist, then that means it's physically impossible for the special administrative privileges granted to proof-of-stake protocols to be decentralized anywhere except exclusively within people's collective imagination. The author is being repetitive because this is a crucially important concept to understand that clearly isn't resonating with the general public. Therefore, the key to understanding the systemic security flaw of proof-of-stake systems like Ethereum 2.0 is to simply recognize upfront that stake doesn't physically exist. Stake is purely an abstraction, a name that Ethereum's developers intentionally gave to the special administrative permissions needed to approve or disapprove Which transactions are allowed on the Ethereum blockchain? Anybody who uses Ethereum 2.0 tacitly requires validation, permission, and approval of the administrators who have abstract stake, aka abstract power. If people with stake choose not to validate a user's valid transaction request, then the user's ability to utilize the blockchain will be degraded, and there is little the user can do to prevent the degradation on their own. As of this writing, 60% of all transactions that have been made on Ethereum 2.0 have been compliant with sanctions imposed by the Office of Foreign Assets Control, OFAC. In other words, 60% of all valid but non-OFAC compliant transaction requests have been deliberately censored by those who have special administrative permissions granted to them by their stake. Thus, almost immediately after switching from proof of work to proof of stake, Ethereum became a majority-censored blockchain where valid users requesting valid transactions, who happen to not be OFAC compliant, are being denied 60% of the time. Clearly, these people's ability to utilize the blockchain has been degraded in comparison to other users, and there is little they can do to eliminate the degradation. According to Ethereum's developers, this type of degradation shouldn't occur because validators should know that degrading people's access to the blockchain decreases the value of the blockchain, yet the attacks are still occurring. Also, according to Ethereum's developers, users have the ability to slash the stake of validators if they censor transactions like this. Yet to date, none of the validators who are censoring non-OFAC compliant transaction requests have had their stake slashed, because to do so would require users to come to consensus via a voting system that stake should be slashed. As always, the problem with voting systems is that voting systems represent yet another form of trust-based, permission-based, and egalitarian abstract power hierarchy. Those who are having their transactions degraded have no ability to project power on their own in a zero-trust and permissionless way to take back the administrative privileges that are being used to degrade them. They are wholly reliant on voters. Recalling the core concepts from the section Creating Abstract Power on Creating Abstract Power to seek permission or social approval from someone, particularly software administrators, is to tacitly give them abstract power over you. On the flip side, if you want to create and wield abstract power over a large population of humans, simply convince them to adopt a belief system where they need permission or social approval from you. Once a population believes they need your permission or approval, you have successfully gained abstract power and influence over them. Bitcoin also couples special permissions to those who solve its proof-of-work algorithms, but because that work is a physically real phenomenon, that is Watts, that means these special administrative permissions, 1, can be physically impeached or countervailed by any user of the network for any reason at any time, and 2, can be physically decentralized across the planet. Neither are true for stake. Despite the fact that it's incontrovertibly true that stake doesn't physically exist, people are making claims that administrative control over Ethereum 2.0 is decentralized. Here, the word decentralized is used in quotes to remind the reader that an abstract software object like stake, which doesn't physically exist, cannot be verifiably decentralized because it isn't a real thing. Since stake is purely an arbitrary semantic description of an abstract object, that means the special administrative permissions given to Ethereum 2.0 validators can only be decentralized in name only. The following point demands to be repeated yet again. It's physically impossible to prove that the special administrative permissions given to those with stake is decentralized, or conversely, that it wasn't already centralized from the very start, because stake doesn't physically exist. The only place that Ethereum's stake can be decentralized is in people's collective imagination. Ethereum's developers claim that stake is decentralized because it has been divided across different validators. However, logically partitioning stake across different addresses or validators doesn't mean those addresses or validators aren't controlled by the same person or group of people, groups like the Ethereum Foundation. So it's impossible to claim that stake is decentralized merely because it has been mathematically partitioned across multiple addresses or across multiple validators. The same person could easily control millions of validators, and the fact that validator node hardware has minimal physical signature actually makes it easier for people to disguise how many validators they own and control. This highlights another baked-in security feature of Bitcoin's hashing infrastructure that some might not appreciate. The fact that Bitcoin's hashing infrastructure consumes so much energy gives it a large physical footprint that's much harder to hide or disguise, thus harder to centralize under one person or organization's control. In other words, the more power that Bitcoin's hashing infrastructure consumes and the more heat that it produces, the easier it is for people across the world to independently verify that it's decentralized. On the contrary, the fact that Ethereum 2.0's validator network consumes so little energy makes it far easier to hide and disguise how consolidated its stake is. The lack of electricity consumption essentially functions as a cloaking or stealth mechanism for people or groups, like perhaps the Ethereum Foundation, who might feel motivated to disguise how many validators are under their centralized control. It's already public knowledge that the majority of stakeable Ethereum was awarded to Ethereum 1.0's founders before it was released to the public. Combining this fact with the fact that stake doesn't physically exist, this means nobody can verify that Ethereum 1.0's founders don't continue to have centralized control over the majority of Ethereum 2.0's stakeable Ethereum. If nobody can verify that Ethereum's founders don't continue to control the majority of stakeable Ethereum, that means nobody can verify that Ethereum 1.0's founders don't already control the majority of Ethereum 2.0's stake. So not only is it physically impossible to verify that stake is decentralized, but there's also no indication to believe, much less verify, that Ethereum's founders don't have centralized control of stake, thus centralized administrative privileges. To make matters even more systemically vulnerable, Ethereum 2.0's staking protocol is designed so that people who have more stake are rewarded with proportionally more stake, and those rewards are compounding. This is an extremely noteworthy design feature. Ethereum 2.0 developers deliberately added additional design logic into the system, which gives the people who have the most stake the most rewards. In other words, the protocol is intentionally designed to give the people who already have the most abstract power even more abstract power than anyone else in the future. The more stake they control today, the more stake they will get to control in the future. The emergent effect of this design logic is that the people who have the most abstract power and control authority over the system today get to keep it forever. Not only that, but the abstract power also grows and consolidates as a higher percentage of the system's total stakeable Ethereum is gradually awarded to them because of the protocol's compounding reward system. The author has now highlighted 5 systemic security vulnerabilities associated with Ethereum's conversion from a proof-of-work system to a proof-of-stake system that are quite easy to recognize. First, proof-of-stake causes people to forfeit their ability to impose severe physical costs on attackers, effectively domesticating users. Second, proof-of-stake is decentralized in name only because stake doesn't physically exist and therefore can't be verifiably decentralized. Third, validator hardware has a minute physical signature, making it easy to hide centralized control over validators. Fourth, the system is intentionally designed to give the people with the most stake today the most stake in the future, thereby consolidating, that is centralizing, stake into the hands of the people who already have the most stake. Fifth, it's already public knowledge that the people with the most stakeable Ethereum could be the people who awarded themselves with the most Ethereum when they originally developed the software, and there's no way to verify they don't continue to have it. Ethereum 2.0 is therefore a decentralized in name-only abstract power hierarchy. Users who accepted the conversion from Ethereum 1.0 to Ethereum 2.0 have adopted yet another belief system that gives people special abstract powers over them and then trusts them not to exploit or abuse it. By coupling special administrative privileges needed to approve transactions to those who have the most stake, A proof-of-stake system removes all of the physical constraints that were keeping those special administrative privileges physically constrained and physically, thus verifiably, decentralized. Now the people who have the most stake have the critical administrative privileges to approve transactions, but that stake is completely imaginary. Switching from proof of work to proof of stake effectively functions as a way to change and then obfuscate which users have the most important administrative privileges and control authority over the system. People buy into this sleight of hand because they don't understand enough about the complexities of computer theory to understand that stake doesn't physically exist and is purely an object-oriented abstraction for what could also be called rank or admin rights. In other words, stake is nothing more than a metaphor for abstract power. People with the most stake have the most administrative privileges to approve or disapprove transaction requests. Thus they wield substantial abstract power. Moreover, we already know that the people who probably have the most stake are Ethereum's core group of developers and co-founders, since they overtly awarded themselves the majority supply of stakeable Ethereum several years ago, and they can't prove they don't still control it. Not surprisingly for anyone who understands power projection tactics in human society, Ethereum developers will argue that Ethereum 2.0 is still systemically secure against exploitation because of the systemically exploitable voting logic, aka slashing, encoded into the software that will ostensibly prevent them from abusing the special authorities given to them by their stake. Users must assume that staked Ethereum isn't already majority controlled by one organization to believe that the voting logic for slashing belligerent stakers will work as intended, which is a blind and unverifiable assumption. Here we have a situation where the people who gave themselves the most abstract power are claiming that users can hold them accountable by slashing their abstract power using a systemically exploitable voting system that they encoded. This would be yet another situation where the people with abstract power try to convince their believers that a belief system is secure against systemic exploitation because of systemically exploitable logic that was encoded into the system to constrain abstract power by the people who have the most abstract power. Remarkably, despite literally thousands of years of written testimony from history, discussed at length in the section Dysfunctions of Abstract Power, to show that design logic, especially voting systems, can't secure a belief system against the exploitation of logic, people accept this argument. To highlight how unique and different Bitcoin is, call it BitPower instead of Bitcoin. To correct the information hiding problem and make it easier to understand the irreproducible properties of Bitcoin, the author suggests using a more technically accurate name for the proofs of power produced by proof-of-work protocols, BitPower. The power part of BitPower refers to quantities of physical power, aka watts, drawn out of the environment over time, modulated, and then digitally sampled by the network of computers running the physical cost function protocol, aka the hashing network. The bit part of BitPower refers to the machine-readable bits of information generated from these sampled watts. Combining these two terms together, the word BitPower literally means quantities of power, aka watts, converted into physically scarce, decentralized, and costly bits of information that can be transferred across cyberspace. Unlike most software specifications, it is important for the reader to understand that the term bit power is not a semantically arbitrary abstraction. The word bit power is meant to be taken literally, not metaphorically like most software abstractions. This is beneficial because the literal definition of bit power doesn't hide critical information about what's happening under the hood of the software at the state mechanism level, like other abstract specifications like Bitcoin do. Bit power refers to the real-world quantities of physical power drawn out of the environment and consumed by the network of computers running the BitPower protocol, which is then converted into machine-readable bits of information that can be passed around cyberspace and called whatever people want to call it. Bit power isn't an imaginary concept designed to make it easier for people to understand a specific use case of the technology. It's literally digitized power. The reason why the term bit power is not metaphorical is because the protocol leverages real-world quantities of physical power, as opposed to transistor states, to transmit, receive, and store bits of information. Like many features of the Bitcoin protocol, the term is a little confusing because it's recursive. Power serves as both the underlying state-changing mechanism and the symbolic meaning assigned to that state change as machine-readable information. When utilizing bit power protocols like Bitcoin, people are not just utilizing state-changing transistors to store bits of information and then arbitrarily choosing to describe those bits of information as some arbitrary metaphor. Instead, they are utilizing real-world quantities of physical power and then choosing to describe the emergent behavior of that real power as digitized power. Bit power, therefore, doesn't technically qualify as hypostatization like coin does. As previously discussed, hypostatization is when people treat an abstract idea as if it were a concretely real thing. When people describe bits of information as abstract objects like coin and then act like those coins are concretely real, they're hypostatizing. On the contrary, the term bit power describes bits of information as something that is concretely real, large quantities of electric power drawn out of the surrounding electric power grid. Bit power is the digitized version of itself that can be utilized by machines inside the digital environment we call cyberspace. This is a subtle but important distinction to call out because it illustrates the previously mentioned concepts about how the coins created by other so-called blockchain or cryptocurrency technologies are highly incomparable to Bitcoin's coins. To make it easy to see how dominant and nearly incomparable the Bitcoin protocol currently is in comparison to other cryptocurrencies, simply call it bit power instead of coin. Using this naming convention, it's easier to see that bit for bit. No other protocol's bits can claim to represent remotely as much physical power as Bitcoin's bit power. As of this writing, Bitcoin represents 94% of the hash rate of all physical cost function protocols combined. Since hash rate doubles as a proxy measurement for the quantity of real-world power consumed by the network and converted into bits of information, this means the Bitcoin network is currently 16 times more powerful than all other proof-of-power protocols combined. The top contenders are currently Dogecoin, Litecoin, Bitcoin Cash, Monero, Ethereum Classic, Dash, and Zcash. This is noteworthy because general public perception of Bitcoin's dominance has been skewed by people who deliberately ignore or attempt to marginalize or condemn Bitcoin's power usage. If one were to ignore or marginalize Bitcoin's power output, or try to arbitrarily categorize it as merely a blockchain or cryptocurrency, then Bitcoin would appear to be one of thousands of cryptocurrencies with no discernible lead. However, if one were to account for the power output and actually recognize it as the primary value-delivered function of the protocol, then Bitcoin is clearly the dominant protocol. Considering how Bitcoin's function could be to produce physically costly bits of information, trying to make a less physically costly version of Bitcoin would defeat the point of Bitcoin. Therefore, those who claim that Bitcoin needs to be more energy efficient could be highlighting their own lack of understanding that the purpose of this protocol is to reverse optimize bits to make them physically costly. Therefore, the repeated attempts to duplicate the Bitcoin protocol which fail to produce the same physical power output of Bitcoin only serve to further show how unmatched Bitcoin is as the dominant proof-of-work network. Michael Saylor, MIT 1987, famously summed this up in 2021 when he declared, "There is no second best." Softwar. World War II will be a guerrilla information war with no division between military and civilian participation. Marshall McLuhan. If these theories are valid, then bit power could be strategically valuable. It's worth repeating that as of today, the concepts presented in this thesis are just theories. However, if these theories hold up to scrutiny within the computer science community, then this would imply that bit power protocols like Bitcoin fundamentally represent a new power projection tactic, a clever way to impose physical costs on other people through their computers by turning physical power itself into bits of information. When someone describes bit power, they are technically describing the real-world emergent properties and effects of physical power in a machine-readable format that can be controlled and projected against others in, from, and through the Internet. If these theories prove to be valid, then it means sapiens have figured out how to harness physical power to increase their CA and lower their BCRA to keep themselves secure when operating in the virtual domain simply by choosing to treat real power as bits of information so that it can be wielded in an imaginary domain called cyberspace. It's a simple concept. To project real power in a virtual world composed of nothing but bits of information, convert power itself into bits of information. Herein lies a core insight about physical costs function protocols like Bitcoin. Adoption of these protocols means entire populations of people are projecting real-world quantities of physical power against each other to impose real-world physical costs on each other, but doing it electrically rather than kinetically and through the cyber domain. Agrarian society appears to be doing this transnationally in a non-lethal way, which doesn't look anything like physical power projection capabilities of the past. This could mean that a global-scale physical power competition is being waged, and nations don't appear to be aware that it's happening because the battlefield is inside the disembodied virtual reality of cyberspace, where nobody can be physically harmed, and things are easily hidden by abstractions and metaphors. If, for the sake of argument, we accept the author's theories as valid, then it begs the question, over what exactly is agrarian society competing? To answer this question, the author will further examine physical cost function design concepts produced by Hal Finney and Satoshi Nakamoto. The Gabriel's horn paradox shows it's logically possible to be infinitely scarce yet infinitely scalable. An important feature to note about Nakamoto's design of Bitcoin is that the bit power it produces is supply-capped, making it perfectly scarce. Paradoxically, that same supply-capped quantity of bit power is also infinitely scalable. Despite having a strictly limited supply, Bitcoin's bit power can accommodate any number of users and convert any amount of real-world physical power into bits. This is a logically counterintuitive emergent property that is made possible by the fact that bit power is digital and therefore has no mass. To better understand how this works, the reader is invited to reflect upon a phenomenon called Gabriel's horn. A popular character who appears in the holy texts of all three Abrahamic religions is an angel named Gabriel. In Catholic traditions, Gabriel is a saint and archangel who wields a horn to herald the Lord's return to earth. Many artistic depictions of Gabriel show him wielding a long and slender heralding horn, and that horn doubles as a symbol of human salvation. In the field of mathematics, Gabriel's horn is the namesake of a special geometric shape. If you plot the function on a two-dimensional graph, chop off the resulting curve from the point where x and y both equal 1, and then rotate the curve across either axis, you get the famous volume of revolution known as Gabriel's horn. The reason why this geometric shape is called Gabriel's horn is simply because it bears a striking resemblance to Gabriel the Archangel's heralding horn. Gabriel's horn, the geometrical shape, is noteworthy because it has special mathematical properties. The volume of space inside the horn is fixed, but the surface area of the horn is infinite. This is a mathematically sound shape that could theoretically exist in three-dimensional reality. If it did exist, the volume of the horn could easily be filled with a fixed quantity of paint, yet its surface could never be completely covered in paint, no matter how much paint someone had. This is a logical paradox known as the Gabriel's horn paradox, aka the painter's paradox. Practical limitations in manufacturing prevent Gabriel's horn from being built, but the point still stands that it's a mathematically sound shape that could theoretically exist in three-dimensional reality. It would therefore be perfectly, but paradoxically logical, to design something with a fixed volume of supply, but infinitely expandable, thus infinitely scalable, surface area. Understanding Gabriel's horn paradox is key to understanding a very important feature of Bitcoin. Because of the logical constraints encoded into Bitcoin's software, the bit power produced by the Bitcoin protocol has the same paradoxical behavior as Gabriel's horn. Bitcoin's supply of bit power has a fixed volume, yet it can scale to accommodate any number of users and any amount of real-world physical power, and do this all while remaining infinitely divisible. No matter how much real-world physical power is consumed by the computers attempting to solve Bitcoin's hash function, the total number of sequentially reusable bits of coin produced by the protocol to account for that power expenditure remains completely fixed. These dynamics create a logical paradox that is difficult for some to understand. The total quantity of real-world physical power, aka watts, consumed and accounted for by the protocol is theoretically infinite, but the total quantity of bit power exchangeable in cyberspace is fixed. At the same time, even though the total supply of bit power remains fixed, an unlimited number of people can have access to infinitely smaller pieces of it that can also account for infinitely larger amounts of power. A single bit of bit power produced by the Bitcoin protocol can scale to represent theoretically unlimited quantities of real-world physical power. And because bits have no mass and are infinitely divisible via logic, then 1. Everyone in the world can access Bitcoin's bit power, and 2. Everyone who accesses any amount of bit power has infinitely scalable physical power projection capacity. Instead of converting a practically unlimited supply of physical power, aka watts, into a virtually unlimited supply of bit power, Nakamoto's design intentionally utilizes the Gabriel's horn paradox. At first glance, Nakamoto's design appears to break the laws of physics. However, the Gabriel's horn paradox proves that the design is mathematically sound. One way to better intuit the paradoxical behavior of Nakamoto's design is to abstract the bit power it produces as surface area on Gabriel's horn, rather than ordinary geometrical shape like a coin. Nakamoto's physical cost function protocol takes an infinitely expandable quantity of physical power drawn from the environment and digitally converts it into a fixed volume of bit power that can account for an infinitely expandable supply of watts. So instead of visualizing Bitcoin's bit power tokens as coins, it might be more appropriate to visualize them as equally partitioned sections of surface area on Gabriel's horn. Now may be a good time to remind the reader that using object-oriented software design, computer programmers arbitrarily describe the complex emergent behavior of computer programs as if they were objects. They do this to make it easier to intuit the complex emergent behavior of their programs, because humans are used to living in a three-dimensional world with objects oriented around each other. This means the choice to describe bit power produced by the Bitcoin protocol as an ordinary object like a coin could just as accurately be described as equally partitioned segments of surface area on Gabriel's horn. Why do this? Because it highlights the protocol's paradoxically logical, complex emergent properties. The conversion of an infinitely expandable supply of physical power into a fixed supply of bit power creates two emergent properties that are important to explicitly call out. The first has already been discussed. Any infinitely minuscule amount of bit power can represent an infinitely large quantity of physical power. This is a useful behavior to have if the goal of the protocol is to maximize the physical cost associated with transferring, receiving, and storing each bit. A second emergent property worth calling out is that Bitcoin's bit power can't be diluted as more physical power is added to the system. Consequently, those who own or control Bitcoin's bit power automatically inherit the strength of all future physical power added to the system in a perfectly equal way. Expanding on these two important features further, since there's no limit to how far the surface area of Gabriel's horn can grow, there's consequently no limit to how far any tiny section of surface area can grow either. This means there's no limit to how much physical power any single amount of surface area can represent. Any infinitesimally small section of surface area on Gabriel's horn can expand or contract to represent any quantity of physical power drawn out of the environment by the computers running the protocol. Thus, There's no theoretical limit to how much physical power can be represented by a bit of bit power, no matter how minuscule the amount. The holder of a single bit of Bitcoin can theoretically project an unlimited number of real-world watts in, from, and through cyberspace. Moreover, even though the addition of more physical power into the system causes the percent magnitude of single units of physical power to decrease, this does not translate into cyberspace as a decrease in the percent magnitude of single units of bit power. The percent magnitude of any amount of bit power remains constant because the total supply of bit power, as represented by the volume of the horn, remains fixed. Instead, the number of watts represented by each unit of bit power must increase to account for more physical power added to the system. The key takeaway from this design feature is that it creates a dynamic where it's not possible to dilute the physical power projection capacity of bit power, no matter how much additional physical power is added to the system. If you own 1 bit of bit power, you own the same percent magnitude of physical cost-imposing power in cyberspace, no matter how much the system scales or how much more physical power the system consumes. This creates a substantial first-mover advantage, as well as substantial path dependence that makes Bitcoin unforgiving to those who hesitate to acquire its bit power. This is another important feature which makes it more of a strategic imperative to position oneself as an early adopter. Combining these two emergent properties together creates a logically sound but paradoxical dynamic that could make Nakamoto's version of BitPower disproportionately valuable as a cybersecurity asset. Recall from the section Physically Resisting Neo-Technocratic God Kings that proof of power, aka bit power, represents proof of physical cost of attack or proof of CA. If the supply volume of bit power is fixed, then owning bit power means automatically inheriting any of the physical cost-imposing power added to the system in the future, with no theoretical limit to how much physical cost any amount of bit power can impose on other people, computers, and computer programs. In other words, owning Nakamoto's supply-capped bit power means being able to leverage infinite amounts of real-world physical power to impose real-world physical costs on others in, from, and through cyberspace, without the capacity for it to be diluted by adversaries in the future, no matter how much it scales. Consider the paradoxical dynamics of how Nakamoto's design converts physical power to bit power. The real-world, infinitely expanding quantity of physical power, aka watts, consumed by Bitcoin's hashing network can be visualized as an infinitely expanding volume taking the shape of a cube. Nakamoto's protocol takes this infinitely expanding volume of power, visualized here as blue cubes, and digitally converts it into a fixed supply volume horn with infinitely expandable surface area that is Gabriel's horn. The left side of this image illustrates the expanding supply volume of physical power drawn out of the environment by the computers running Nakamoto's protocol. This is represented as a cube with volume expanding towards infinity. If we were to isolate 1 unit of that cube's volume and measure its percent magnitude as the total volume of the cube expanded towards infinity, then we would see the percent magnitude of that single unit of volume gradually fall to 0. In this image, we can see that the percent magnitude of 1 watt of physical power drops from 5% to 0% as the overall volume of electric power drawn out of the environment expands from 20 watts to infinity watts. Nakamoto's design digitally converts this volume of physical power into information, bit power, that is logically constrained as if it were the surface area of a Gabriel's horn. Here we can see how the digital representation of bit power in virtual reality can be implemented as infinitely expandable surface area on a fixed volume Gabriel's horn geometry, in contrast to the geometry of an infinitely expanding cube with infinitely expanding volume. This sleight of hand is possible because bit power is digital, that is disembodied or massless. If we were to isolate 1 segment of that horn's surface area and measure its percent magnitude over time as the total surface area of that horn stretched towards infinity, then we would see the percent magnitude of that single segment of horn surface area remain fixed. In this illustration, we can see that the percent magnitude of one segment of horn surface area remains fixed even as it expands towards infinity. The bottom line is that Nakamoto's design creates a paradoxical but mathematically valid behavior that causes the protocol's bits to have unique and counterintuitive properties that are perhaps easier to intuit if visualized as sections of surface area on Gabriel's horn rather than ordinary objects like coins. By visualizing a bit power as if it were a segment of surface area on Gabriel's horn, it perhaps becomes easier to understand the paradoxical behavior caused by digitally converting infinitely scalable quantities of real-world physical power into a fixed supply of bit power. The most important takeaway of this design concept is that an infinitesimal amount of bit power can represent an infinitely large quantity of physical power for any number of users without dilution, giving it potentially disproportionate strategic value as a cybersecurity asset that is both infinitely scarce and infinitely scalable. This creates an unforgiving first-mover advantage and path dependence that is important for people to understand. Bit power could function as digital age freedom fighting technology. We can win a major battle in the arms race and gain a new territory of freedom for several years. Satoshi Nakamoto, summarizing the core theoretical concepts about bit power presented so far. Bit power protocols like Bitcoin look inefficient to those who might not understand the complexities of computer theory, cybersecurity, agrarian power dynamics, human metacognition, or the basics of how living organisms establish dominance hierarchies to manage control over their resources. Consequently, people don't understand how and why people would be inclined to summon large quantities of electric power from the environment, convert it into machine-readable bits of information, and use it for systemic security purposes, particularly to countervail the threat of people wielding too much abstract power via the computers they program. As theorized in previous sections, the electric power deficits produced by proof-of-work protocols appear to turn the global electric power grid into a planetary-scale state-changing mechanism that can transmit, store, and receive machine-readable information, thus adding a physically constrained and thermodynamically restricted state space to cyberspace with complex emergent properties that are physically impossible for ordinary computers to replicate. A physically constrained and thermodynamically restricted state space within cyberspace is a novel capability that appears to have been missing from cyberspace thus far, and society appears to be starting to grasp the broader social, technical, and strategic security implications of this capability. This thesis is proof. The bottom line up front is that for the first time, people appear to have discovered how to project physical power in, from, and through cyberspace by converting global power itself into bits. Thanks to protocols like Bitcoin, people can utilize bits of information that have been reverse optimized to be physically expensive to produce, to impose severe physical costs on belligerent actors who keep trying to interfere with people's bits or systemically exploit people through software. These physically expensive bits could also be used to prove the presence of real-world properties such as scarcity and decentralization in an otherwise artificial domain where ordinary computers can only be programmed to present the illusion of scarcity and decentralization. One clear application for this capability is security against cybercrime and cyber tyranny. Bit power protocols make it possible to project physical power in a unique way to keep oneself secure against computers, computer programs, and computer programmers by physically constraining them. Rather than having to rely on permission-based abstract power hierarchies which can only logically constrain certain unsafe or exploitable control actions by giving only a few people with high rank and special administrative privileges the permission needed to execute them, software engineers now have a way to design control structures which can apply physical constraints and use physical power, not abstract power like rank or admin rights, as the basis for establishing control over software. Just like animals in nature and people in agrarian society leverage the systemic benefits of physical power to settle disputes, manage resources, and establish dominance hierarchies in shared objective reality, bit power protocols like Bitcoin theoretically make it possible for people to utilize this exact same strategy in cyberspace. We can now settle disputes, establish control authority, and determine the legitimate state of ownership and chain of custody of bits the old-fashioned way, through real-world physical power competitions. And remarkably, we can do it without causing injury because the protocol utilizes electric, that is non-destructive power, rather than kinetic, that is destructive power. Using bit power protocols like Bitcoin, which convert real power into digitized power to wield in a digital domain, it is theoretically possible to design physical power-based resource control structures that physically constrain unsafe or insecure control actions and physically constrain people with abstract power. No longer do people have to design systemically exploitable abstract power hierarchies created by computer programmers that give special permissions to specific people and trust them not to abuse it. This is important because logically constrained software control structures and software-defined abstract power hierarchies are demonstrably prone to systemic exploitation, either externally via hackers or internally via abusive system admins or insider threats. Accelerating cybercrime incidents have demonstrated how challenging software security is when people don't have the ability to impose physical constraints. We have discussed how it's impossible to logically constrain something against the exploitation of logic, whereas it's easy to physically constrain something against the exploitation of logic, simply make it impossible to justify the physical cost of exploiting logic. We may be starting to see these same principles hold true for the emergence of cyber tyranny. There's no clear way to escape from massive-scale systemic exploitation of our software exclusively by writing more lines of code. The root cause of cyber tyranny would be the same as the root cause of our challenges with cybercrime. Users have no way to physically constrain or thermodynamically restrict the abstract powers of software administrators who are abusing the trust we must necessarily put into these people not to exploit us through our bits. If we are to mitigate the threats of cybercrime or cyber tyranny, it's necessary for us to adopt some type of protocol which will empower people to secure their bits physically by projecting physical power in, from, and through cyberspace to impose severe physical costs on those who exploit our computing systems. And that's precisely what the Bitcoin protocol is doing. Physically countervailing oppressive abstract power hierarchies is the American way. The United States gained its independence by imposing severe physically prohibitive costs on high-ranking people who were exploiting them through their abstract power hierarchy. Thanks to Bitcoin, Americans now appear to have gained the same capability of digital freedom fighting for cyberspace. Of course, the threat of tyranny and the need for revolution was not just exclusive to Americans. Agrarian society has suffered through several millennia of systemic exploitation from people creating, wielding, and abusing their abstract power. Revolutions make it clear that societies must remain capable of and willing to project physical power against their ruling class if they want to keep themselves secure against systemic exploitation, abuse, and oppression from their ruling class. A major difference between revolutions of the past and revolutions in the digital age is the technology used to exploit people and to physically resist that exploitation. The digital age ruling class is the technocratic group of people who control our computers through the software they write. It's the people who administer our software, including but not limited to governments. In previous chapters, we explored how self-domestication is a real threat. Society's lack of ability or inclination to project physical power in any domain to reduce their BCRA is a well-known systemic security hazard that can be independently and empirically validated. The exact same systemic security hazard exists for cyberspace. Without the capacity or inclination to project physical power and impose physical costs in, from, and through cyberspace, a technocratic ruling class of neo-god kings have an opportunity to domesticate and systemically exploit human populations at a massive and unprecedented scale, simply by having physically unconstrained control authority over their computer networks. Fortunately, electro-cyber power projection protocols like Bitcoin, people now appear to have the technology they need to countervail this threat. People could use this technology to countervail abstract power hierarchies when they inevitably become too exploitative. This technology could become instrumental to the design of different control structures or computer networks which make it impossible to justify the physical cost of exploiting people through their software. If these theories are valid, then the only thing preventing our digital age global society from starting to physically secure themselves against the emerging threat of cyber tyranny is for them to 1. Recognize the threat, 2. Recognize they have this capability, and 2. Start using it. From the perspective of power projection theory, it seems inevitable that we are going to have a digital age revolution, a soft war for zero-trust, permissionless, egalitarian, and decentralized control over our worldwide web of computers. As Nakamoto himself declared, Bitcoin is part of an arms race which could help people gain new territory for freedom for years to come. The author hypothesizes that agrarian society is now beginning to recognize that they have the capacity to project power in, from, and through cyberspace to secure themselves against the threat of systemic exploitation of their computer networks. The technology appears to be hiding in plain sight by masquerading as a peer-to-peer electronic cash system. To that end, the purpose of this thesis is to illustrate how physical cost-function protocols like Bitcoin represent far more than just monetary technology. They represent physical power projection technology. And if history is any indicator of what's to come, the emergence of a new form of physical power projection has the potential to be far more unique, valuable, disruptive, and strategically essential than a new form of money, especially as the global population continues to spend exponentially more time using computers. The socio-technical and national strategic impacts of Bitcoin envisioned by the author have little to do with finance. This is not a grounded theory about money, it's a grounded theory about power. The author asserts that the Bitcoin protocol is first and foremost a physical power projection protocol, and bit power represents the ability to physically countervail abstract power and resource control authority of software administrators and physically decentralize the cyber empires they're trying to lock people into via cyberspace. This not only impacts businesses, but it also impacts governments. Because of proof-of-work technology, entire populations are now literally empowered to impose real-world physical costs on other people and programs via cyberspace, to include computer programs controlled by governments. Agrarian society can now strategically secure itself against innumerable attack vectors encoded, often intentionally, by any type of computer programmer, regardless of who they work for. Therefore, the author asserts that Bitcoin is not monetary technology, at least money doesn't appear to be its primary value-delivered function. Instead, Bitcoin appears to be an electro-cyber freedom-fighting technology. In other words, Bitcoin isn't a monetary protocol, it's a bit power protocol. It creates a new base layer foundation to the Internet by adding a new state mechanism to the bottom of the Internet tech stack, which physically constrains the worldwide web of computers. And it just so happens that the first use case for this novel Internet infrastructure is financial payments. But it's reasonable to expect there will be far more use cases to follow. In what could have been an intentional sleight of hand, and perhaps one day be reflected upon as the most impressive Trojan horse since the Trojan War, the decision to frame Bitcoin as only a peer-to-peer electronic payment system has motivated transnational human society to subsidize the development of a global-scale electro-digital defense industrial complex that literally empowers people with zero-trust, egalitarian, and permissionless access to bit power. Extraordinary quantities of physical power are now being drawn from a planetary-scale state mechanism and converted into physically costly bits of information that anybody can utilize to impose severe physical costs on people and programs in, from, and through cyberspace. With this new internet architecture, people are capable of physically securing themselves against hackers, as well as physically securing themselves against systemic exploitation from an emerging technocratic ruling class. And they can do it all without spilling a single drop of blood. Power projection theory is a bold theory, but it's a grounded theory. It blends military theory, political theory, and computer theory together using first principles and systems thinking. If power projection theory proves to be valid, then Bitcoin represents the emergence of a new internet tech stack which disrupts our perception of cyberspace from the bottom up. It's also a non-lethal form of freedom fighting that could empower people to physically resist tyranny and oppression in, from, and through cyberspace. By simply calling it a coin, this freedom-fighting technology has blossomed and grown under the noses of those who made the classical mistake of expecting the next revolution to look like the last revolution, a vital new resource worth fighting for. Physical power can and has been used to establish zero-trust and egalitarian control structures which can't be systemically exploited like abstract power hierarchies can. The systemic exploitation of abstract power hierarchies has been a problem that has plagued society for thousands of years, and software-defined abstract power hierarchies are just as vulnerable to exploitation as abstract power hierarchies like governments are. Bit power protocols have a chance at counteracting the hazards of abstract power hierarchies, just like physical power has already done for thousands of years. If someone were to design an open-source protocol where everyone has zero trust, egalitarian, and permissionless access to bit power, it could be extraordinarily valuable as a cybersecurity asset. With these concepts fresh in our minds, the author will now revisit the design of the physical cost function protocols designed by Back, Finney, and Nakamoto. As outlined in the previous two sections, attaching bit power, aka proof of work or proof of power receipts, to sensitive control actions issued by a computer program makes it possible for engineers to design new types of control structures which can physically constrain the execution of virtually any control signal in cyberspace, making them too physically costly to systemically exploit and thus more systemically secure. This is a compelling security capability that appears to have been missing in computer science until the emergence of physical cost function protocols, aka proof of work or bit power protocols, like the one built by Back. The first iteration of Back's bit power protocol issued non-sequentially reusable bit power that were stamped onto individual control actions for one-time use. This design requires computers to consume electricity and solve the hash cost function for every individual control signal that the protocol was used to physically constrain. This presents a technical problem. It makes any computer program utilizing the protocol run too slowly to be practically useful. If people had to wait several minutes for a computer to solve a difficult hash function algorithm every time they wanted to issue a command, then the protocol would likely not be adopted because of how impractical it would be to use. Recognizing this technical issue with Back's bit power protocol design, a computer engineer named Hal Finney created a more practical version of a bit power protocol where the proof of power receipts, aka proofs of work, are sequentially reusable. That way, instead of having to wait for a computer to solve the hashing cost function each and every time someone wanted to send a command, they could simply present a proof of power token to show that the hash cost function was solved at some time in the past. Finney understood that a sequentially reusable version of bit power would have the same effect of imposing severe physical costs on the computer trying to execute a command, but it would remove the lag of having to resolve the hash cost function for every new command. It's worth noting that this was not a new idea. This is precisely what Jules and Jacobson described as a bread pudding protocol in their 1999 paper, which introduced the term proof of work. The main difference is that Finney actually built it, whereas others theorized. Using the same naming convention created by Jules and Jacobson and adopted by Back, Finney called his design concept Reusable Proofs of Work, RPOW. The bottom line is that a major advantage gained from Finney's sequentially reusable bit power protocol was speed. In Back's design, bit power is destroyed after the execution of a single command. At scale, this creates an impractically slow system where the hashing algorithm must be solved to execute every new command. When bit power is sequentially reusable, it becomes possible to make a much faster and more practically useful system while still preserving the primary value-delivered function of physically constraining computers by imposing severe physical costs on the execution of specific commands. Another major advantage gained from Finney's reusable proof-of-work design concept was that his version of bit power could be used as a general-purpose proof-of-power protocol that could serve multiple different use cases rather than exclusively one application at a time, such as reducing email spam. Finney described this advantage as follows. Normally, proof-of-work tokens can't be reused because that would allow them to be double spent, Finney writes. But reusable proof-of-work allows for a limited form of reuse, sequential reuse. This lets a proof-of-work token be used once, then exchanged for a new one, which can again be used once, then once more exchanged, etc. This approach makes proof-of-work tokens more practical for many purposes and allows the effective cost of a proof-of-work token to be raised while still allowing systems to use them effectively. Theoretically speaking, a single bit of sequentially reusable bit power can be utilized an infinite number of times for any number of different use cases. It could also be sequentially reused at such a high frequency that it could be visualized as a continuous stream of irradiating bit power rather than individually discrete transfers of bit power. Reusable bit power protocols therefore have very attractive qualities that could serve multiple applications. Unfortunately, as is the case with most engineering design decisions, the benefits gained from making bit power sequentially reusable also introduces a tough design challenge. By making bit power tokens reusable, Finney had to figure out a way to enable sequential reuse while simultaneously prohibiting parallel reuse. Parallel reuse is a problem because if bit power can be reused in parallel, it would effectively defeat the purpose of the protocol. Each bit power would no longer be able to impose severe physical costs on computers because they could be duplicated ad infinitum, driving the physical cost associated with each bit power token down to zero. As a side note, this is the same reason why there has to be a hard cap on the supply of bit power that is Bitcoins. Sequential reuse of bit power doesn't undermine the laws of thermodynamics, but parallel reuse does. Power can be transferred, stored, and reused in series, but it cannot be created or destroyed, therefore it can't be cloned or exist in two places at once. Considering how bit power's value is derived from its physical constraints, then allowing parallel reuse of bit power would logically undermine its value. The utility of proof of power is derived from the fact that the physical power expended to produce bit power is physically expensive, in watts, and thermodynamically restricted. This reverse optimization is what makes bit power unique and gives it its irreproducible emergent properties. A custodian who can reuse bit power in parallel is someone who effectively has the ability to reproduce or clone real-world physical power out of thin air and then use it in two places at once. These custodians would be breaking the real-world constraints of physics that are ostensibly imposed by the protocol, making them false or fraudulent representations of real-world physical power in cyberspace, hence one of the many reasons why people claim that alternative systems like proof-of-stake are fraudulent. Remember, the point of these protocols is to reverse optimize bits to make them physically expensive to transmit, receive, and store. If these bits can be used in parallel, or there are not hard limits on their supply, or they are extraordinarily energy-intensive to produce, then that defeats the point of the protocol. To mitigate the problems of parallel bit power reuse, Finney had to figure out how to design a protocol which enables sequential reuse of bit power while simultaneously constraining parallel reuse. From a systemic design perspective, this is exactly the same challenge that financial systems have. Financial systems must figure out a way to enable the sequential reuse of monetary notes while prohibiting parallel reuse, a form of fraud where users make counterfeit bills or deliberately write checks they can't cash. The financial community calls this the double spend problem. If we were to arbitrarily abstract bit power as coins, then we could say that Finney's primary design challenge was the same challenge faced by financial systems, finding a way to solve the so-called double spend problem. In order for Finney's reusable proof-of-power protocol to function properly, it would require the addition of a third step to the physical cost function protocol that Back's version didn't have, keeping track of the position of each bit power coin over time to make sure they're only reused in series, not in parallel. In other words, Finney's physical cost function protocol had to instantiate a ledger which keeps track of the legitimate state and chain of custody of each bit power coin to make sure they weren't being used in two places at the same time. Finney's solution to the double spend problem, the same way financial systems solve the double spend problem, by having a trusted party keep account of the position of each bit power token to ensure they're not being used in two places at the same time. Unfortunately, this design choice introduces a significant systemic security vulnerability. It requires trust in a group of people with special permissions not to abuse their special permissions to exploit the system. In other words, Finney's design implemented yet another form of abstract power hierarchy, where people with imaginary power, in the form of special administrative permissions to add transactions to the ledger, have control authority over bit power and its state of ownership and chain of custody. Like all abstract power hierarchies, this is a trust-based and inegalitarian resource control design which creates a ruling class of administrators and a ruled class of users. The ruled class must trust their ruling class not to abuse their special permissions because users are otherwise physically powerless to countervail them. Having just read hundreds of pages explaining how abstract power hierarchies are systemically insecure no matter how they're encoded, hopefully the reader can now appreciate why Finney's bit power protocol design was flawed from a systemic security perspective. Finney's reusable bit power protocol design was flawed for the exact same reason that governments or any other form of abstract power hierarchy is systemically flawed. They're trust-based, permission-based systems which give people abstract power and control authority over a vital resource and trust them not to exploit it for their own personal advantage, despite an ever-increasing benefit for doing so. We have more than 5,000 years of written testimony which says that abstract power hierarchies break down and become dysfunctional no matter how well they're designed and no matter what logical constraints they try to impose through their rule sets. Bit power has the potential to be an extraordinarily valuable resource. By creating a ledger which keeps track of the legitimate state of ownership and chain of custody of each bit power token, to allow for sequential reuse and prevent parallel reuse, then restricting access to writing the ledger to a trusted third party, Finney created an abstract power hierarchy where some entity has abstract power and control authority over the entire system by virtue of their having control authority over the ledger, accounting for the position of each bit power token. His protocol created yet another abstract empire where users must trust in a technocratic elite class of computer programmers not to exploit their control authority over a potentially vital resource. Finney's design introduced useful features to bit power protocols like sequential reusability and the ability to pseudonymously register ownership of bit power using private key encryption. But at the same time, the system relied on a trusted third-party server to keep account of the position of each bit power token. Therefore, even though Finney's design successfully solved the double spend problem and introduced other useful features, the way the system solved the double spend problem had a glaring systemic security vulnerability, a vulnerability that a pseudonymous software engineer named Satoshi Nakamoto was quick to point out and resolve. Let those with real power compete for zero trust and permissionless control over ledger writing. Administrative privileges in a way that can decentralize that control. Inspired by Back and Finney's design concepts, Nakamoto's design created sequentially reusable bit power and also accounted for the sequential state of ownership and chain of custody of bit power using a ledger just like Finney's design did. However, the primary difference was that Nakamoto's design didn't logically constrain ledger-writing administrative privileges to a trusted server wielding imaginary power. Instead, Nakamoto chose to assign these special administrative privileges to those who demonstrate they have real power, aka Watts. Instead of creating an abstract power-based dominance hierarchy to manage the ledger, Nakamoto created a system where people with real-world physical power, aka Watts, engage in a global-scale physical power competition for ledger-writing control authority in a zero-trust, permissionless, and egalitarian way. As a complex emergent benefit of this global-scale physical power competition, the special privilege of writing the ledger remains decentralized and always impeachable, thereby empowering users with the ability to remain physically secure against systemic exploitation and abuse of those ledger-writing privileges. Because physical power is unbounded, there is theoretically no limit to how many watts people can project to countervail the power of any other person or organization who might attempt to exploit or abuse these special ledger-writing administrative privileges. Herein lies the cleverness of Bitcoin's design. The Bitcoin protocol empowers society to leverage physical power to battle for control authority over a potentially vital new agrarian resource, bit power. Through this global-scale power competition, agrarian society decentralizes control authority over the ledger and achieves consensus on the legitimate state of ownership and chain of custody of bit power in a zero-trust, egalitarian, and permissionless way. By simply giving permission to write the ledger to those who win the physical power competition, Nakamoto solved the double spend problem in a way that doesn't make people as vulnerable to systemic exploitation and abuse of software administrators. With this simple design concept, the BCRA of the Bitcoin ledger writing privileges drops down to the point where it's impossible for attackers to justify the physical cost of attempting to exploit these privileges. The complex emergent benefit of this global-scale physical power competition for ledger-writing administrative privileges is decentralization of control over bit power. In what could be described as an impressive display of design thinking, Nakamoto replicated the complex emergent benefits of warfighting by creating an electro-cyber version of it. He created a system where globally divided populations with completely different priorities and belief systems can engage in a physical power competition to establish control authority over this potentially vital resource and achieve global consensus on its legitimate state of ownership and chain of custody in a purely zero-trust, permissionless, and egalitarian way. To that end, what makes Bitcoin's design remarkable is not merely that it solved the so-called double spend problem or the so-called Byzantine generals problem. What makes Bitcoin remarkable is that it appears to have created a non-lethal equivalent to warfighting that achieves the same complex emergent benefits of traditional warfare using the exact same social protocol of engaging in a physical power competition, but it removes the mass, thus eliminates the capacity for human injury. The way Nakamoto solved the Byzantine generals problem could solve much bigger problems. Using power projection theory, the author argues in this subsection it's not that Bitcoin solves the Byzantine generals problem which makes the protocol so special, it's how it solves this problem. Nakamoto didn't just create a monetary protocol, he created a global-scale electro-cyber warfighting protocol where humans engage in a planetary-scale physical power competition to establish pecking order over a vital resource, bit power, in a zero-trust and egalitarian way, all without causing injury to humans. In other words, Nakamoto didn't just create a peer-to-peer electronic cash system, he appears to have invented a human antler protocol. Nakamoto is given credit for solving the double spend problem without having to rely on a trusted third party to account for the chain of custody of sequentially reusable bit power. To accomplish this, he designed a system which utilizes a distributed network of nodes to manage the ledger rather than relying on a trusted third party, a glaring security vulnerability with Finney's design. Of course, Nakamoto's decision to utilize a distributed network to manage the ledger introduced another design challenge. How do you get a distributed network of computers that can't be trusted to agree on the legitimate state of the ledger? In computer science, this challenge is what's known as the Byzantine generals problem. Because Nakamoto's protocol provided a viable solution to this challenge, Nakamoto is given credit for solving the Byzantine generals problem. However, the author asserts that crediting Nakamoto's Bitcoin protocol for solving the Byzantine generals problem undersells how significant it is. Using the core concepts of power projection theory, we can better appreciate why Nakamoto's design could be far more significant than merely solving a distributed computing challenge. This technology also has the potential to also solve a much bigger challenge faced by society as a whole, a global strategic nuclear stalemate that is preventing nuclear superpowers from settling strategic-level disputes about their most valuable resources and policies, including, but not limited to, their financial resources. The design challenge which Nakamoto faced was the age-old challenge of establishing zero-trust, egalitarian, and permissionless access to a resource. Whoever has administrative authority over a bit power ledger implicitly gets control authority over people who depend on bit power. That control authority can be exploited. The ability to add transactions to the ledger doubles as the ability to deliberately withhold transactions from the ledger. This means the ability to add transactions to the ledger doubles as the ability to denial of service, DOS, attack users. By simply choosing not to add valid transactions requested by a given user, that user can be DOS attacked. Just by gaining permission to write the ledger, an entity gains a form of abstract power over people in the form of special permission, which they can exploit to deny someone access to their property. Determining who gets to write the ledger therefore represents an extremely sensitive control action with major systemic security implications, which must be property constrained by a control structure design. From a broader systemic perspective, we can see that the problem Nakamoto faced with determining how to establish ledger-writing control authority over the bit-power ledger was not merely a problem faced by computer scientists working with distributed computing networks. This is a problem that has been plaguing human society for thousands of years. This is a problem that life itself has wrestled with for the past 4 billion years. People miss this critical insight because they frame Nakamoto's design challenge as this: how do you get a distributed network of computers to agree on the legitimate state of the ledger? But an equally accurate way to frame Nakamoto's design challenge has far bigger scope. How do you establish control authority over a resource in a zero-trust, egalitarian, and permissionless way that doesn't utilize a systemically exploitable abstract power hierarchy? Establishing zero-trust, egalitarian, and permissionless control authority over a resource is fundamentally a question about how to settle disputes without the use of abstract power like rank. This is fundamentally a question about achieving consensus between strangers without a judge, or a god-king, or some other kind of person wielding abstract power derived from permissive authority. For at least 10,000 years, sapiens have done this the same way animals do it, using a physical power projection protocol we call warfare. The problem Nakamoto faced with determining how to establish zero-trust and egalitarian control authority over bit power is therefore not merely a challenge faced in distributed computing. This is a challenge that sapiens have encountered since at least the dawn of the Neolithic age. Sapiens have been struggling to figure out a zero-trust and permissionless way to manage valuable resources and establish pecking order without injuring each other, and they have never succeeded to date. The most they have been able to achieve is creating temporary and fleeting reprieves from the destruction and injury of warfare. They have never been able to remove the destruction and injury of warfare altogether. If Nakamoto successfully solved the challenge to which he's often given credit, that could not just mean he solved a core challenge in computer science. That could mean he solved a core challenge for agrarian civilization. He created a non-lethal form of war fighting. In other words, he created soft war. It is difficult to understate how big a deal it would be if it were true that Nakamoto did indeed discover a way for global society to achieve zero trust, egalitarian, and permissionless control over bits of information passed across the internet. Because that would mean he figured out a way for global society to establish zero trust, egalitarian, and permissionless control authority over many of digital age society's most precious resources without requiring kinetic warfare. From this perspective, the fact that people have arbitrarily decided to call the bits of information secured by the Bitcoin computing network a coin seems trivial in comparison to the fact that Nakamoto may have discovered how to build a soft war protocol that society could use to decentralize the internet and physically countervail the abstract powers and control authorities of those who are systemically exploiting its current architecture. The core concepts of power projection theory bear repeating. Humans already know how to establish zero trust, egalitarian, permissionless, and decentralized control authority over resources. We have already developed a protocol where different populations of people who can't trust each other settle disputes and achieve consensus on the legitimate state of ownership and chain of custody of resources without the use of trusted third parties wielding some form of abstract power that is rank, admin rights, server owner, and control authority in some form of abstract power hierarchy. Society already knows how to leverage physical power in an inclusive, unbounded, and systemically exogenous way to achieve decentralized control authority over resources. The protocol is called war fighting. Therefore, what makes Bitcoin special isn't just that it allows for a bunch of people across the world to establish zero trust, egalitarian, permissionless, and decentralized control over precious resources, because we already do that with warfare quite effectively. Hence why Earth's natural resources are split across 195 different countries. What makes Bitcoin special is how it achieves this same end state. It doesn't it electronically through cyberspace rather than kinetically through sea, land, air, or space. If it is true that Nakamoto solved the problem he is given credit for solving, then that could imply he also solved a much bigger, much larger scope problem that has been plaguing society for thousands of years. The problem of how to establish control authority over precious resources, how to settle disputes, how to establish dominance hierarchies, and how to achieve global consensus between people and nations alike concerning the legitimate state of ownership and a chain of custody of property, and do it all in a way that requires no god-kings, no bloodshed, and thus alleviates the threat of mutually assured destruction. Bitcoin is zero trust, permissionless, and decentralized control over a precious resource, itself. This section summarizes all of the concepts discussed so far. Bitcoin appears to be a globally adopted physical power projection protocol, or soft war protocol. The first war that agrarian society appears to be fighting. Using this soft war protocol is a war to determine who has control authority over bit power, as well as a war to establish consensus on bit power's legitimate state of ownership and chain of custody. Just like other resources that agrarian society routinely fights over, for example land, the complex emergent effect of this soft war is decentralization of control over bit power, where people are free to compete for access in a zero-trust, permissionless, and egalitarian way. But unlike other battles, this one is completely non-lethal. The term bit power is not a metaphor like other software specifications. Bit power is, quite literally, bits of information created by state changes of physical power created by society through their global electric power grid. By doing this, the Bitcoin protocol utilizes society's power infrastructure as a planetary-scale computer that isn't under the consolidated control of a single person or organization. The bits of information created by this planetary-scale computer are unique in comparison to other bits of information on the Internet because they're reverse-optimized. In a world where bits are becoming exponentially less scarce and less physically costly to produce, bit power is designed to become exponentially more scarce and more physically costly to produce. This gives bit power unique emergent properties that are irreproducible by ordinary computers running ordinary computer programs. By developing APIs which require computer programs to utilize bit power, it is impossible to impose severe, physically prohibitive costs on people and their programs in, from, and through cyberspace. This capability has the potential to make bit power quite valuable for applications like cybersecurity or situations where computer programmers want to produce real-world physical properties like physical scarcity or decentralization, rather than producing virtual illusions of physical scarcity or decentralization. It is already incontrovertibly true that proof of work works for cybersecurity because Bitcoin uses this proof of work to keep its own proofs of work secure against systemic exploitation. This can be confusing to some people because it's recursive. Bitcoin is proof of its own merit as a cybersecurity system. Using the Bitcoin Softwar protocol, people are projecting real-world quantities of physical power to earn the right to account for the legitimate state of ownership and chain of custody of each sequentially reusable bit of bit power. As a result of this electric power competition, aka Softwar, the protocol is proving itself to be capable of making it physically impossible for anyone to justify the physical cost of exploiting it, even the most powerful nations in the world. This is how Bitcoin demonstrates its own merit as a cybersecurity system which can physically countervail cyber attacks, not strictly a monetary system. It is clearly working as a new type of power projection technology which allows people to include entire nations to keep the bits of information encompassing the property and policy they value secure against attacks by empowering them to impose severe, physically prohibitive costs on belligerent actors which may or may not include nations. As demonstrated by Admiral Columbus and his plot to convince native Jamaicans to forfeit their resources to his crew, who had been oppressive to their Jamaican hosts, there is nothing limiting a person or a crew of people from exploiting a population's belief system to give themselves centralized and unimpeachable control authority over the population's resources, except for one thing: the physical power competition they would have to win against people who refuse to allow their belief systems to be exploited. This highlights a complex, emergent social benefit of warfighting that many overlook. War physically prevents people from creating, encoding, consolidating, and centralizing abstract power and control authority over resources by exploiting a belief system. This is especially important to note in the 21st century because software fundamentally represents a belief system that is highly vulnerable to exploitation. Therefore, the author asserts that warfighting is valuable to society because it gives people the opportunity to engage in global-scale physical power competitions to physically constrain and decentralize the reach of people with too much abstract power and control authority over resources. We know this is true because we know that warfare is the reason why control over Earth's natural resources is currently decentralized across 195 different nations. Bitcoin takes this exact same type of global power competition, but converts it into an electric form rather than a kinetic form. Bitcoin therefore clearly functions as an electro-cyber war-fighting protocol. People are using Bitcoin to create and compete for zero trust and permissionless access to a scarce and irreproducible supply of reverse-optimized bits of information that can be transferred, received, and stored via cyberspace, but remain under no organization's centralized or unimpeachable control. Why would digital age society want a soft war protocol? to preserve their freedom of action in the international thoroughfare we call cyberspace, to preserve their access to the bits of information they value, to protect and defend their ability to pass bits of information across cyberspace in a way that can't be interfered with or systemically exploited by people wielding and abusing their abstract powers over computers. The physically secured bits of information that are being passed across proof-of-work computing networks like Bitcoin could potentially represent a vital new resource that 21st century society could need to combat cyber tyranny and keep themselves physically secure while operating in cyberspace. To that end, proof-of-work protocols like Bitcoin could give people the freedom to fight for zero trust and permissionless access to their most valuable bits of information, the same way they have always fought for zero trust and permissionless access to their most valuable resources. Proof-of-work protocols offer the same might-is-right pecking order heuristic that has been battle-tested by 4 billion years of natural selection. And those who learn how to project physical power in the most clever and resourceful way win the right to write the ledger to account for those bits. The physical power competition for access to and control over Bitcoin's bit power not only keeps the system decentralized and secure, it also makes the issuance and consensus mechanism unbiased. Like physical power itself, the Bitcoin protocol makes no ethical, moral, theological, or ideological judgments about those who use it. This makes Bitcoin both perfectly fair and perfectly aligned to nature's proven method for settling disputes, managing resources, and establishing pecking order. This is the same method agrarian society already uses to establish their dominance hierarchy over Earth's limited resources, despite how much they like to use their imaginations and role-play like they don't. Mutually assured preservation. The US dollar enjoyed great trust around the world, but for some reason it began being used as a political weapon, imposing restrictions on use. They began to bite the hand that feeds them. They'll collapse soon. Many countries in the world are turning away from using the dollar as a reserve currency. They restrict Iran in its dollar settlements. They impose some restrictions on Russia and other countries. This undermines confidence in the dollar. Isn't it obvious? They're destroying it with their own hands. Vladimir Putin, securing trade routes and preserving freedom of action in a new thoroughfare, cyberspace. One of the core functions of a military is not to secure a nation's borders, but to secure a nation's trade routes. The US Navy, for example, exists to secure trade routes and preserve freedom of action in, from, and through the maritime domain. In whatever domain a nation relies upon to exchange goods, they tend to need a military to physically secure their ability to exchange goods and preserve freedom of action in that domain, else they become vulnerable to denial of service attacks. Imagine if the entire ocean was under the complete control of a single organization, and every nation who wanted to exchange goods across the ocean tacitly needed the permission of a single organization to do it. Would it be reasonable to believe a single organization in control of the entire ocean can be trusted not to exploit their control? Would it be reasonable to expect other nations to be pleased with a situation where they must have the tacit permission of one organization to access the ocean, establish trade routes, and exchange goods? The answer to these questions is probably not. Yet, this trust-based, permission-based system is exactly how cyberspace currently functions. We have established that computers are state machines. A network of computers connected together creates a state space which transfers, receives, and stores bits of information. Some call this state space an intranet or internet. Others call it cyberspace. Because these are abstract names, it would be just as accurate to call cyberspace an ocean. This ocean, created by a network of computers, functions as a new domain through which nations exchange a vitally important new type of good: bits of information. Over the span of a single human lifetime, this cyberspace ocean has become a very important domain upon which nations rely for the exchange of vital bits of information. Many different bits of information have value, but among the most valuable bits of information that nations like to exchange are bits of financial information which facilitate international trade and settlement. Right now, the ocean through which nations exchange most of their bits of financial information is under the complete control of a single organization. This extraordinarily asymmetric amount of abstract power and control authority is derived from the fact that one nation controls the network of computers facilitating the exchange of these bits of information. The organization which has administrative control over this network has abstract power over the vital bits of information transferred, received, and stored on it. This abstract power gives them complete, unimpeachable, and centralized control over this entire ocean that many of the world's nations rely upon for the exchange of some of their most vital goods. If any nation wants to use this ocean to set up trade routes and exchange their highly valuable financial bits of information on it, they tacitly rely on the permission of a single organization to do it, and they must implicitly trust that organization not to exploit their control over the domain to inhibit their freedom of action. This system of information exchange between nations is currently a trust-based, permission-based, and inegalitarian system that is clearly vulnerable to exploitation. The US has conclusively demonstrated this by denial of service attacking Russia from telecommunications network, such as the one controlled by the Society for Worldwide Interbank Financial Telecommunications, SWIFT. This begs a question. Why would any self-respecting nation who wants to have sovereign access to information exchange across the cyber domain subscribe to a permission-based system like this, when those permissions can be revoked at any time? One explanation could be that they simply don't have a viable alternative. It's hard to think of any computer used in telecommunications which aren't under the unimpeachable control of some group of people. There might not be a viable way for nations to exchange bits of information using a telecommunications network without relying on a computer network that's still under some group's permissive controls. In this scenario, if a nation were to be denial of service attacked by SWIFT, for example, they would have no choice but to adopt some other computer network to exchange their bits of financial information. The challenge, of course, is that the other network would be equally as systemically insecure as SWIFT, because it would still be under the permissive control of some other group of people. With the current architecture of the Internet, there doesn't seem to be a way that nations can use computer networks and not be vulnerable to this form of exploitation. This would change if a planetary-scale computer were connected to the Internet, over which no organization could gain and maintain complete or unimpeachable control. If society were to adopt a protocol like Bitcoin that leverages the globally distributed electric power grid as a planetary-scale state mechanism over which no single person, organization, or nation can physically afford to have centralized and unimpeachable control, then the state space of that state mechanism would represent a special new thoroughfare which nations could utilize to exchange their most valuable bits of information in a zero-trust, permissionless, and egalitarian way. Nations could theoretically use this planetary-scale computer to set up their digital trade routes, passing all bits of information they want to keep secure against denial-of-service attacks and other systemic exploits. It would be in a nation's best interest to set up something like this, considering how it's always been the responsibility of government to keep trade routes open and preserve freedom of action in every domain they operate. There's simply no reason to expect the cyber domain to be an exception to other domains in this regard. Herein lies one of the most critical insights of Bitcoin that might be overlooked. If the technical theories presented in this thesis are valid, and it's true that proof-of-work protocols like Bitcoin utilize the global power grid as a planetary-scale computer, which adds a special new state space to the existing state space of the Internet, then that new state space could represent the first truly zero-trust, permissionless, and egalitarian digital trade route in cyberspace that nations may come to rely upon to exchange their most valuable bits of information. An obvious first use case for this technology is to preserve the freedom of exchange of financial bits of information needed for international trade and settlement, but there would be several additional use cases. How might nations physically secure their ability to exchange their most valuable bits of information and preserve their freedom of action in this new, strategically advantageous trade route within the cyber domain. Perhaps the same way they already do for land, sea, air, and space, by utilizing their specialized group of physical power projectors called the military to impose severe physical costs on those who impeded their freedom of action. With this concept in mind, the reader is invited to consider how some nations have already begun to adopt the Bitcoin network to exchange valuable bits of financial information needed for international trade and settlement. El Salvador is even raising bonds to subsidize the development of their own portion of the Bitcoin network, which converts their country's geothermal power into bit power. By doing this, El Salvador is actively working to secure zero-trust, egalitarian, and permissionless access to this special part of the Internet under no organization's centralized and unimpeachable control. And they're actively demonstrating to other nations that it's working at keeping their valuable bits of information secure. Based on the precedent set by El Salvador, one could argue that nations are beginning to see how strategically vital it is for them to physically secure their access to this special piece of the Internet where other nations can't prohibit them from exchanging their bits of information. To secure access to this unrestricted place in cyberspace against foreign interference, nations appear to be learning that they must create services dedicated to the projection of real-world physical power in, from, and through cyberspace, just like they already do for land, sea, air, and space. Nations appear to be learning how vulnerable they are to denial-of-service attacks by the system administrators of the computer telecommunications networks they choose to use. The actions taken by organizations like SWIFT against Iran and Russia have showcased to the world that whoever controls the network of computers managing the valuable bits of information they rely upon tacitly has complete and unimpeachable control over them. Nations may be beginning to see that a zero-trust, permissionless computing network that enables bits of information to be transmitted, received, and stored without the threat of denial-of-service attacks or other forms of systemic exploitation are a vital national strategic security priority, not just for financial bits of information, but for any kind of bit of information. This would imply that Bitcoin could become widely recognized as a national strategic security imperative. El Salvador's actions demonstrate that nations are already beginning to recognize Bitcoin as a candidate solution. If Bitcoin were to be adopted by other nations, that could validate it as a systemically secure and strategically important computer network. To date, no nation has been able to surmount the enormous physical cost required to denial-of-service attack or systemically exploit Bitcoin's bits, including and especially nuclear superpowers. That's noteworthy, and nations appear to be taking notice. Why build an electro-cyber militia when you can just subscribe to one? If the author's theories on Softwar are valid, then national adoption of Bitcoin could be envisioned as the adoption of an electro-cyber militia to protect and defend a nation's valuable bits of information. Nations like El Salvador are creating their own hash force, a service dedicated to projecting physical power to preserve their country's freedom of action in, from, and through cyberspace by imposing severe physical costs, aka watts, on anything that seeks to deny their sovereign right to freely exchange bits of information. But even if El Salvador didn't elect to build their own hash force by simply choosing to use the Bitcoin network as the domain through which they exchange their financial bits of information, El Salvador would still be inheriting the security capabilities of the Bitcoin network as if subscribing to a military-grade physical security-as-a-service protocol. From a systemic perspective, Bitcoin functions similarly to how a militia functions. A large group of people project lots of physical power to preserve freedom of action within a particular domain, giving nations the ability to exchange goods, in this case bits, with another nations without interference. The form of the militia is different because the form of the domain is different. Cyberspace is disembodied and transnational, so it makes sense that a cyber militia would be disembodied and transnational too. Something remarkable about the disembodied and transnational form of Bitcoin's security infrastructure is that it appears to be highly resistant to kinetic strikes, including strategic nuclear strikes. Bitcoin's infrastructure is spread across the world and is comprised of the globally distributed internet, power grid, and all the people running these systems. Because it's a decentralized network, the only way to destroy it is to destroy the whole network. This would suggest that the only way to destroy the Bitcoin infrastructure is to destroy both the internet and the global electric power grid. While this is theoretically feasible, it's not practically feasible because of the kinetic power projection paradox discussed in the section Humans Need Antlers. Our species would likely go extinct sooner than we would be able to destroy all of the physical infrastructure of the internet and the global electric power grid. We may technically have the capacity to destroy Bitcoin's infrastructure, but because of the kinetic power projection paradox, it appears to be too expensive to do. In other words, the BCRA of destroying Bitcoin is simply too low to justify. Therefore, not only do nations gain the physical security benefits of a global-scale electro-cyber militia when they adopt the Bitcoin network as the means through which they exchange bits of information on the internet, they also appear to gain free access to a non-lethal security system that is, at least practically speaking, impervious to nuclear strike. In other words, nations which adopt Bitcoin gain access to a global-scale physical defense infrastructure that can empower them to stand up to nuclear-armed superpowers. Raising hash forces to preserve zero trust and permissionless access to the Bitcoin network. With new physical power projection capabilities come new national strategic security strategies. In Bitcoin's case, nations now, at least theoretically, have a way to ensure that certain organizations in charge of certain telecommunications networks, for example SWIFT, cannot abuse their abstract power and control authority over the network to denial of service attack nations who have a sovereign right to freely exchange bits of information across the internet. And because Bitcoin's physical power projection technology is electric rather than kinetic, this new strategy doesn't appear to be limited by the kinetic power projection paradox. This could mean that Bitcoin represents a key enabling technology for a new national strategic security strategy that could overcome a nuclear stalemate. For the sake of argument, let's assume the theoretics presented in this chapter are valid, and that the bits of information exchanged via the Bitcoin network do indeed represent reverse-optimized bits of information that are physically costly to transmit, receive, and store, giving them unique properties that are useful for many applications. Let's assume that securing zero trust, egalitarian, and permissionless access to these special bits becomes increasingly recognized as a national strategic opportunity. Any nation that follows in El Salvador's footsteps in adopting the Bitcoin network as the domain through which they exchange bits of information would also inherit the same baked-in physical security benefits of Bitcoin's global-scale, nuclear-resistant defenses. These nations would effectively be subscribing to the security services of Bitcoin's globally decentralized electro-cyber militia, the same way a nation does when it subscribes to another nation's military for defense. It's a cost-effective strategy, but it's also a trust-based and permission-based strategy. By subscribing to Bitcoin's cyber militia as is, without contributing their own physical power and hashing infrastructure, a nation would tacitly be trusting in that militia not to denial of service attack them. The possibility exists that everyone participating in the network could unite against a given nation and withhold their valid transaction requests. Fortunately, the easy way to prevent this threat is for a nation to have their own hash force. This would allow them to utilize their own physical power projection capacity to guarantee they maintain ledger-writing permissions. In effect, a nation would be building their own electro-cyber militia and attaching it to Bitcoin's combined electro-cyber militia to preserve permissionless access to the network. If this scenario were to play out, it would represent a global-scale international soft war for access to the Bitcoin network and its underlying bits of information. But unlike other global-scale international wars, a Bitcoin soft war would have far different strategic dynamics that would lead to a much different end state. The author calls this special end state mutually assured preservation, solving the kinetic power projection paradox. As discussed at the end of the previous chapter, sapiens have a knack for building highly efficient power projection technologies which empower populations to win physical power projection competitions called wars. After more than 10,000 years of practice perfecting the craft of physical power projection, sapiens appear to have reached a stalemate due to what the author calls the kinetic power projection paradox, a situation where society has become so efficient at a particular method of kinetic power projection that it is paradoxically too inefficient to use because of how much mutual destruction it would cause. To date, strategic nuclear warheads appear to be the most efficient kinetic power projection capacity ever invented by sapiens in terms of size, weight, and effort. Unfortunately, this technology is so efficient at projecting massive quantities of physical power that it does not appear to be practically useful. A full-scale war between two nuclear-armed nations would most likely be a war without winners. It's hard to solve a dispute if both sides are mutually destroyed. Ironically, the most efficient kinetic power projection technology ever created, nuclear warheads, appears to have created the most inefficient way to settle international policy disputes. Nations tacitly validate the existence of a nuclear stalemate caused by the kinetic power projection paradox when they pursue far less efficient kinetic power projection strategies to settle their disputes, manage control authority over resources, and determine consensus on the legitimate state of ownership and chain of custody of their property. Instead of using highly efficient power projection technologies like tactical nuclear bombs, they use non-nuclear weaponry like kinetic munitions to settle their disputes. Since the discovery of nuclear power, this strategy of deliberately using less efficient non-nuclear power projection technologies has only succeeded at settling minor disputes between asymmetric powers. It's still not clear whether it's actually possible for two nuclear-armed nations to settle major disputes using non-nuclear power projection technology. This would require one nation to be willing to surrender to another, despite having the capacity to mutually assure the destruction of the nation to which they're surrendering, and that doesn't seem like a realistic scenario. It seems far more likely that a nation would sooner accept a stalemate than surrender to a nation they could destroy. And nuclear warheads are what give nations the former option rather than the latter. However, even if we assume that it's still possible for two nuclear-armed nations to settle a major dispute without using nuclear technology, this doesn't resolve the kinetic power projection paradox or bypass the risk of mutually assured kinetic destruction. Forking the evolutionary path of kinetic power projection technology development into a non-nuclear direction still leads to the same dead end. By attempting a fork, modern society would likely continue to do what they have done so demonstrably well in the past and develop incrementally more efficient kinetic power projection capabilities until they discover yet another way to mutually destroy each other, except this time without nuclear warheads. Therefore, the strategy of using deliberately less efficient, non-nuclear kinetic power projection technologies seems likely to cross the same threshold as nuclear technology did, where it becomes too efficient to be practically useful, aka crossing the kinetic ceiling. A speculative example of a kinetic power projection technology that could follow nukes in crossing the kinetic ceiling is massive-scale swarms of millions of highly maneuverable, artificially intelligent killer drones. It seems unlikely that two nations would be able to utilize kinetic physical power competitions to solve major disputes or secure access to resources in a zero-trust, permissionless, and egalitarian way if both sides of the conflict had access to strategic nuclear missiles as well as command over swarms of millions of highly intelligent killer drones. This situation seems like it would easily lead to another stalemate at both the strategic and tactical levels using both nuclear and non-nuclear technology. Interestingly, Bitcoin appears to solve this paradox. Global-scale physical power projection competitions enabled by Softwar protocols like Bitcoin appear to be able to solve this type of quagmire by bypassing the kinetic power projection paradox altogether. By using a non-destructive form of electric power rather than a highly destructive form of kinetic power, hash forces would theoretically be able to compete for permissionless access to valuable resources exchanged across the Bitcoin network without the threat of mutually assured destruction. Nations would theoretically be able to increase their electro-cyber power projection capacity and efficiency ad infinitum without it becoming too destructive to be practically useful. No matter how competitive an electro-cyber power competition gets, it seems unlikely that it could lead to a state of mutually assured destruction because there's nothing inherently destructive about developing increasingly efficient forms of electric power projection technology. In fact, society could potentially benefit from this power competition. It would motivate society to search for increasingly more clever technologies to generate more power more efficiently, as well as develop faster and more efficient hashing computers. Whereas the byproduct of a kinetic war is destruction of infrastructure and more expensive energy, the byproduct of Softwar appears to be the creation of more infrastructure and cheaper energy. This makes perfect intuitive sense using the theoretics presented earlier in this chapter. By turning the globally distributed power grid into a planetary-scale computer, society would theoretically be able to unlock Moore's law for the global electric power grid. Society would continually compete for incremental advantages by increasing the power projection efficiency and capacity of their portion of the global electric power grid, that is the portion of the planetary computer circuitry under their direct control. As a result, society could see exponential growth in both the efficiency and capacity of their power grids, just like they already do for their ordinary computers. Bitcoin falls directly in line with the evolutionary path of human power projection technologies developed across the past 10,000 years of agrarian warfare. But more notably than that, Bitcoin represents the only globally adoptable physical power projection technology that is practically useful for nations to settle major policy disputes, including but not limited to international financial policy disputes, establish zero trust control over valuable resources, including but not limited to financial information, achieve global consensus on the legitimate state of ownership and chain of custody of property, including but not limited to digital property, and preserve freedom of action and exchange of goods across cyberspace, and do it all beyond the limit of the kinetic ceiling, where kinetic power projection competitions are no longer practically useful. Combining these observations with the fact that running a hash force can be a profitable endeavor due to the high monetary value that people assign to underlying bits of information exchanged across these networks, this means proof-of-power protocols like Bitcoin paradoxically have the potential to represent the most powerful and efficient physical power projection technologies ever discovered by agrarian society. Physical cost function protocols like Bitcoin make pragmatic sense. If it is true that society is already stalemated at a nuclear strategic level, then why go through the hassle of building a bunch of killer drone swarms to do battle with other killer drone swarms, while humans watch from the sidelines? Are those drone fights going to achieve any meaningful advantage or resolve a nuclear stalemate? If society insists on trying to settle policy or property disputes using human-out-of-the-loop drone swarm battles, then what is the point of making it a kinetic battle? Why not just put the drones on a rack, plug them together, and have them battle each other using electric power through cyberspace rather than kinetic power through three-dimensional space? Technically speaking, Bitcoin is an international power competition between drone swarms. Instead of having machines compete against each other using kinetic power in the air, land, sea, or space domains, Bitcoin's machines are placed on a rack and they compete against each other using electric power in the cyber domain. It's the same game, but in a different domain, a domain that doesn't risk nuclear annihilation and doesn't appear to be stalemated. If the author's observations are valid, then it could mean that protocols like Bitcoin could effectively function as humanity's antlers. This technology could theoretically bypass the kinetic power projection paradox and give nations an opportunity to physically compete against each other in a zero-trust, egalitarian, and permissionless way that isn't stalemated and doesn't cause injury, which means it could generate very clear winners and very clear losers. By bypassing the kinetic power projection paradox, Bitcoin could represent humanity's ticket out of a potential bounded prosperity trap. Escaping a fiery hellscape with a new method for zero-trust cooperation and physical security. During kinetic physical power projection competitions, that is traditional warfare, there is an existential imperative for agrarian society to sum their physical power projection capacity together using cooperation techniques. Cooperation is first and foremost a physical power projection strategy which allows a population to increase their mutual CA to decrease their mutual BCRA. Cooperation has enabled agrarian society to buy themselves increased prosperity margin and deter aggressors over thousands of years. These are the foundational primordial economic dynamics behind national strategic security. The massive-scale abstract power hierarchies, that is, nation-states, we have today are the result of thousands of years of agrarian society learning how to cooperate at increasingly higher scales to keep themselves more physically secure against neighboring abstract power hierarchies. Today, agrarian society utilizes transnational power alliances where multiple nation-states sum their physical power projection capacities together. However, like cyanobacteria and photosynthesis, sapiens and the abstract power hierarchies they build can backfire by causing society to become increasingly more vulnerable to systemic exploitation and abuse through their mutually adopted belief systems. Abstract power hierarchies inevitably break down for reasons discussed at length in the previous chapter. The general problem is that abstract power hierarchies are fundamentally trust-based cooperation techniques. Populations which utilize abstract power hierarchies must adopt trust-based belief systems where people are given abstract power and trusted not to use it against their own populations. The larger and more asymmetric an abstract power hierarchy becomes, the more its believers become vulnerable to systemic exploitation and abuse. Trust-based belief systems are systemically insecure belief systems. Eventually, there is a point where the benefit to breaking people's trust is disproportionately higher than the cost of doing so. These inherent security flaws are important to note because today's nation-states are larger and more asymmetric than ever experienced by agrarian society. Today, it is not uncommon for 99.9999% of the population living within a nation-state to have to trust less than 0.00009% of the population not to abuse the abstract power and control authority appointed to them. This is a highly inegalitarian system that is vulnerable to systemic exploitation. Untrustworthy systemic predators would have much to gain if they wanted to exploit the high-ranking positions of these abstract power hierarchies, and there would be minimal physical cost for doing so, especially if the ruling class has the nuclear launch codes. It is no secret that trust-based abstract power hierarchies have a well-documented tendency to break down and drive agrarian society back to war. War is highly energy efficient and injurious, but it is the only zero-trust, egalitarian and permissionless system where people are free to reset their dominance hierarchies by engaging in physical power competition. Therein lies the tragedy of agrarian society. The more society tries to avoid war, the more they must adopt systemically insecure, trust-based, inegalitarian, permission-based cooperation systems like abstract power hierarchies, which tend to break down and lead directly back to war. Like cyanobacteria, agrarian society appears to be stuck in a bounded prosperity trap, which has driven it to the precipice of strategic nuclear annihilation. Now, populations are being cornered into adopting trust-based abstract power hierarchies with no ability to countervail their ruling classes if they become untrustworthy, exploitative, oppressive, or tyrannical. The emergence of new physical power projection technologies like Bitcoin fundamentally disrupts these power dynamics. Physical cost function protocols like Bitcoin give agrarian society the ability to sum their physical power projection together to increase their mutual CA and decrease their mutual BCRA without having to trust each other. Instead of having to adopt systemically insecure, trust-based abstract power hierarchies to cooperate at larger scales and sum their physical power projection capacities together to impose increasingly more severe physical costs on aggressors, physical cost function protocols like Bitcoin allow people to perform the same function in a zero-trust way. With physical cost function protocols like Bitcoin, anyone who contributes physical power to the system, as measured by hash rate, automatically increases the mutual CA and decreases the mutual BCRA of all users, including adversaries. The author hypothesizes this is because Bitcoin users technically utilize the same planetary scale state mechanism. By turning the global electric power grid into a planetary scale computer, two adversarial users living on opposite sides of the world stick together in a symbiotic relationship because they are technically utilizing two sides of the same machine. Because they're both using the same planetary scale computer, if both sides were to attempt to marginalize the permissions of the other side by building larger and more powerful hash forces, they would increase the CA and lower the BCRA, the same machine upon which they mutually rely. So long as no single hash force is allowed to gain and maintain majority hash rate, which is easy to prevent when all users have the freedom to add theoretically unlimited amounts of physical power or hash rate to the system from their side of the planet, then the addition of more physical power or hash to the system serves to increase the total physical cost required to gain and maintain systemically exploitable control over the system. In other words, as more physical power is added to the Bitcoin network by hash forces, the total physical cost required to achieve centralized control authority over the network increases, making it harder for any one entity to gain and maintain centralized control over the ledger. This creates an emergent behavior of the Bitcoin protocol where the physical costs required to exploit the ledger can grow ad infinitum. No matter how much physical power is summoned by people in the competition for ledger-writing administrative privileges over the Bitcoin network, the protocol can absorb all of it and channel it all towards increasing the total physical cost required to exploit the system. Nations could raise hash forces to secure their own permissionless access to the Bitcoin network. As they compete against each other for permissionless access to the ledger, all users directly benefit from the higher total hash rate and power consumed by the network, including and especially adversaries. Adversaries become mutual beneficiaries because they're both contributing to different sides of the exact same planetary scale machine, which neither side can fully control. The protocol sums their physical power projection capacity together to create a single cost of attacking the network as a whole, causing nations to directly benefit from their adversaries' physical power projection efforts, even though they are directly competing against each other. The more people and organizations use their hash forces to compete against each other for permissionless access to the ledger, the more physical power and hash rate is required for any single hash force to gain and maintain centralized, thus exploitable, control over it. The more they compete against each other and add more hash, the more secure both parties become against denial of service attacks. It's a simple but remarkable emergent behavior of the system. Returning back to a core concept in power projection theory introduced in Chapter 3, cyanobacteria were able to escape from the fiery hellscape of the Great Oxidation Event by evolving several new power projection tactics, to include learning how to stick together using multicellular cooperation. Both types of early multicellular cooperation represented zero-trust cooperation tactics. Cells didn't stick together because they trusted each other. They stuck together because they were literally stuck together either through colonization or clustering. As a result of their zero-trust cooperation tactic, they were able to sum their combined physical power and escape their bounded prosperity trap together. Fast forward by about 2 billion years, and we arrive at modern human society trapped in what could be described as another fiery hellscape. This time, it has taken the form of 10,000 years of agrarian warfare, escalating all the way up to the threat of nuclear annihilation. With soft war technologies like Bitcoin, society could have discovered a technology which enables zero-trust cooperation. By utilizing the same planetary-scale computer, two adversaries who have no capacity to trust each other can mutually benefit from each other's physical power projection efforts. They can use electric power to compete for zero-trust, permissionless, and egalitarian access to a vital new resource, bit power, and bit power itself allows them to impose theoretically unlimited physical costs on each other in a non-lethal way through a virtual domain. By fighting against each other using this soft war protocol, they paradoxically cooperate. Herein lies what the author believes to be the most compelling feature of the Bitcoin protocol. It could create an infinitely prosperous organism as first discussed in section Chasing Infinite Prosperity. By competing against each other for permissionless access to the Bitcoin network, adversaries serve each other by increasing the physical cost required to attack the network. Their competing power projection capacity is summed together to increase the overall CA of the network. As a result of this ongoing power competition, network BCRA perpetually decreases. As users scale their hash rates ad infinitum, the network CA increases ad infinitum and BCRA decreases ad infinitum, thus giving all users an infinitely expandable prosperity margin. So long as no single user can gain and maintain majority hash, everyone using this computer network benefits from the battle over control authority over it. As if by magic, the Bitcoin protocol turns adversarial physical power competition into a single, cohesive, infinitely prosperous organism, chasing after the same mutually beneficial end goal of improving security and preserving freedom of information exchange across cyberspace. Enemies become frenemies. Adversarial nations become de facto collaborators working together on the same planetary-scale computer, despite not trusting each other. Unlike the dynamics of kinetic power projection competitions, the end state of this global-scale electro-cyber power projection competition is not mutually assured destruction, it's mutually assured preservation.